Somewhere out there, in the vast expanses of space, there exists a mysterious comet that, according to astronomers and scientists, should not have the right to exist at all. This has been discussed for a long time, and until recently it was believed that such celestial bodies were merely fantasies or myths born of imagination. However, science continues to surprise us with its discoveries, and it is precisely recently that new, truly sensational information has emerged, capable of overturning all our notions about the universe. It all began with the work of an international team of scientists who used a satellite designed to observe transits of distant exoplanets, called TESS, for their research. And it was on October 14, 2025, that the results of a large-scale analysis they conducted were published, having processed more than 9,000 images obtained from this satellite. These data, acquired using the latest technologies, allowed them to draw conclusions that previously seemed impossible. The new information essentially sheds light on the existence of the so-called 3IATLAS, mysterious interstellar objects that appear to defy the usual laws of astronomy and raise many unanswered questions. Now, thanks to the collection of over 9,000 images, scientists have been able to confirm, for the first time in a long while, the hypothesis that such objects do indeed exist, and that their appearance and behavior have been hidden or carefully concealed, possibly intentionally. These new findings, published within the scientific community, give us a chance to understand what was concealed behind the curtain of secrets surrounding the 3IATLAS, and what exactly has intrigued not only astronomers but the entire world. Today, together with you, we will try to provide a definitive answer by understanding the essence of this discovery, in order to forever solve the mystery that has remained unresolved for centuries. But beyond this cosmic enigma, far from the noise of news and sensationalism, beyond the limits of our knowledge and understanding, there is a very strange star. It is unique in that every 44 minutes it emits radio waves and X-rays, and no one knows exactly why this happens. This mysterious star continually piques scientists' interest and frustrates them, as its behavior seems completely unpredictable and inexplicable. Could this be a new, unusual type of cosmic object that has not yet been categorized among the known? It is possible that this star, with its unusual characteristics, is part of some new chapter in the development of astronomy that has only just begun. At the same time, scientists continue to monitor 4 major coronal mass ejections, powerful streams of plasma currently moving toward Earth. Their approach causes concern, as the consequences of their impact could manifest as severe magnetic storms, solar flares, or even power outages. All signs indicate that this week we may feel and see the consequences of these cosmic events in real life. These natural phenomena will inevitably affect our planet, and their development arouses considerable interest and concern among specialists. Additionally, within this cosmic kaleidoscope, we cannot ignore the ghostly particles, so-called neutrinos, that recently broke all records for their energy strength. These particles, which penetrate through all matter, struck the Earth with an energy previously considered impossible for such objects, opening new horizons in understanding elementary particle physics and interstellar processes. Their power and unusual behavior prompt scientists to rethink existing theories and view the universe from a new perspective. All of this is just part of the mysteries and enigmas that scientists will have to unravel, and what we discover together in the near future has the potential to radically change our perception of the surrounding world. Stay with us until the very end, because what we uncover during this research will not only expand our knowledge, but the phenomenon detected by TESS turned out to be so extraordinary that it literally disrupted our usual worldview. What she discovered could be called more of a mystery than a typical astronomical object. Primarily, the object appeared as a tiny point, like a bright spark, lacking any extended tails or diffuse clouds of dust and gas that usually disperse through space. There was no long tail stretching behind the object toward the sun, nor any signs of dispersed particles forming the characteristic glow of comets. When scientists measured its radial brightness profile, they found that the light emanating from this source decreased with distance from the center in a pattern typical for a star, not a comet. That is, its brightness diminished just like a well-known star, which is a point source due to its great distance. Even considering that stars appear point-like because of their remoteness, shrinking to a single pixel in observations. Their sizes compress into 1 pixel, whereas comets are objects with structure, featuring long tails and extended, cloud-like formations. These comets, which have caused awe and wonder for centuries, possess a pronounced extent that makes them recognizable and memorable. The scattering function of a point source is a characteristic that shows how light from a point source is refracted through a telescope's optical system, and each instrument has its own. It's like a fingerprint, unique and allowing us to understand exactly what we are observing. When the team conducting test observations on 3 similar objects examined them, they saw only one and the same pattern, nothing more. This meant that nothing other than this point source was observed there. The analytical team, after carefully examining the collected data, was able to precisely determine what it all meant. If there had been enough dust in the environment for its brightness to exceed a certain threshold, it would have become detectable by the instruments. However, this did not happen. The process of signal overlay, which increases the signal-to-noise ratio, amplified the faint details so much that even the most inconspicuous features should have surfaced. Yet, despite this, dust was either absent or present in such minimal amounts that it could not be detected. Based on the data obtained, the specialists established limits on dust density, particle size, and ejection velocity. All these parameters pointed to a single, very important fact: the dust present in this object behaves completely differently from typical cometary dust. But this leads to a contradiction, as other observations made with different instruments showed quite the opposite. It is this inconsistency that adds even more mystery to the situation. For example, the James Webb Space Telescope detected water vapor and carbon dioxide around this enigmatic object. Spectroscopic measurements confirmed mass loss and the release of volatile substances, signs of activity characteristic of comets. Everything indicated that this object behaves like a real comet, displaying typical signs of activity associated with sublimation and gas ejection. But a very important question arises. Where is the long, visible tail that should accompany this process? Where are the clear signs that material is truly escaping into space, forming the characteristic trailing clouds of a comet? Here, a complex puzzle presents itself to the scientists. Either the coma, the cloud of gas and dust surrounding the nucleus, is so compact and dense that it remains invisible to our optical telescopes, while still retaining its gaseous signatures, or something entirely different is happening. It's as if observing a bright bonfire that somehow does not produce any smoke or ash, smoke being the obvious evidence that fire is burning. The digital data we obtain from observations not only do not match each other but also show active and, one could say, even hostile contradictions. These discrepancies are not minor errors or random deviations easily explained by measurement imperfections or slight differences in observation conditions. No, this is a profound, fundamental disagreement regarding the very nature of the object we are studying. Today, all the necessary data for analysis are accessible to anyone. Any internet user can download them, conduct their own analysis, and verify the accuracy of the results. And interestingly, the repeatability of these experiments confirms the reliability of the obtained information. One of the key conclusions is that the absence of the expected tails in objects is a convincing fact that leaves no doubt. It prompts scientists to investigate what is happening, because if traditional physics of comets and other celestial bodies cannot explain the observed phenomena, then alternative, more exotic or radical explanations will have to be sought. But before delving into the core of the matter, it is important to understand the scale and nature of these contradictions, as well as the reasons why different instruments produce such contrasting images of the same object. The second part of our story is dedicated precisely to these discrepancies between various observation tools and methods. For example, consider the famous James Webb Space Telescope, or JWST, which is regarded as the pinnacle of modern infrared astronomy technology. It is one of the most advanced and expensive observatories built in recent years, with mirrors assembled from tens of billions of tiny segments. Imagine how this giant turns its mirror surfaces toward the sky, for instance, toward an area that can be conditionally called Atlas III. The observations obtained with this instrument are characterized by exceptional clarity and detail. In the infrared range, it detects the presence of various molecules, such as carbon dioxide and water vapor, and also studies gas comas rich in volatile substances. The spectrometers integrated into JWST capture molecular signatures, characteristic emission lines that indicate excitation and vibrations of atoms and molecules. These signals allow us to determine that molecules are not stationary but vibrate and move through space outside the core of the object. While the telescope observes these processes, other instruments, such as ground-based optical telescopes, record a completely different picture. Sometimes they detect symmetrical structures or nothing significant at all, raising questions and casting doubt on the uniformity of the data obtained. Why does this happen? Why do some instruments detect bright molecular activity, while others see nothing or only static symmetry? The answer lies in the fact that each instrument measures different aspects of the same object. For example, the James Webb Space Telescope operates in the infrared range, which covers wavelengths at which molecules emit light by vibrating and rotating. It is highly sensitive to the presence of gas and its chemical composition around the core of the object, even without needing to see reflected sunlight. It listens to the music of molecules singing in infrared ranges, and these sounds are loud and clear enough for analysis. At the same time, the SPHEREX mission, which also operates in the infrared range, reported an unusually large amount of vaporized carbon dioxide around 3 comets, designated conditionally as ATLAS, with a ratio of carbon dioxide to water that, even by the standards of strange and unusual comets, seemed very high. In contrast, optical telescopes operate differently. They detect reflected sunlight as well as sunlight scattered by dust particles that return to us. To observe structures such as the comet's tail or other features, it is necessary to have an abundance of dust and particles around the nucleus. These larger dust grains, which can sometimes be observed near asteroids or comets, have the ability to hover close to the object, creating a compact yet very faint optical shell. This thin film or layer, although seemingly invisible at first glance, still significantly influences the perception of the object because its presence causes a noticeable amount of gas to form. The reason for this is that ice on the surface of dust particles sublimates when exposed to sunlight, transforming directly from solid to vapor and creating a gaseous environment. As a result, gas is constantly released near such dust particles, even if the dust itself remains almost invisible. Additionally, the geometry of observation plays an important role. The phase angle is the angle formed between the sun, the object, and the observer. It determines how we see the structure of the tail or coma, as well as how their shape and brightness are perceived. Viewing the object from an incorrect angle can make an existing tail appear shortened or almost invisible. It may be directed almost straight at us or, conversely, away from us, which significantly complicates its detection. Consequently, even with an active tail, it can be missed or mistaken for a minor feature if the viewing angle is unfavorable. Different observational instruments used at various times and positions in different orbits record the object from different angles. This adds further complexity. One telescope may observe a prominent tail, while another may not see it at all, simply because the object was at different angles relative to Earth and the Sun during observations. In such cases, it may seem as if the same object has contradictory characteristics, although the real reason lies in the specifics of geometric visibility. It has already been documented that measurement results often differ, which greatly complicates understanding the true structure and activity of a comet or asteroid. For example, the comet ISON, discovered in 2013, was expected to become a very bright and impressive object. However, shortly after its appearance, it disintegrated, and observations showed varying levels of activity. Some telescopes detected strong emission of gas and dust, while others observed minimal activity. A similar pattern was seen with comet C2017K2. In some observations, it appeared highly active, with prominent tails and dust jets, while at other times it seemed almost calm, with no noticeable signs of activity. This sparked debates among scientists. Was the comet truly active, or was it simply periodically releasing gas and dust in short bursts? The question was about the scale. Could minor activity or isolated outbursts produce such effects? The characterization of this phenomenon becomes even more complex when we talk about observing specific objects. For example, the object atlas exhibits not just changes in activity levels or appearance but shows a dual picture. Sometimes it displays bright tails, then they completely disappear, or it appears as a point source with a bright spot against the background of space, and at other times it seems to be a stretched, elongated body. In most cases during observations, it is very difficult to encounter intermediate states, as these transitions are either very abrupt or not detected at all. Additional complexity arises because observations made at different times often contradict each other. The same objects have been observed at different periods with different instruments. For instance, the James Webb Space Telescope recorded events within specific time windows, while ground-based observatories observed at other times. TESS, in turn, could monitor an object continuously but with lower resolution and accuracy. And what if the activity of the object is periodic or short-lived, meaning it releases dust and gas not constantly but intermittently? Then some instruments might detect it in an active state. Now we have approached one of the most mysterious and, at the same time, most important topics related to this space project. It concerns observing a spacecraft that could provide us with the key to unlocking many secrets. The whole idea would seem very enticing. If we had an instrument capable of delivering flawless images, excellent resolution, precise geometry, and correct orientation, then we could see what the mysterious atlas truly looks like up close. Such an instrument exists. It is the Psyche mission. This spacecraft was launched to study the metal-rich asteroid of the same name. Its trajectory could bring it into a zone where it would be visible from Earth or orbital platforms, providing an opportunity to take detailed images that could shed light on many uncertainties. But where are these images? Why have they not been published yet? After all, the Psyche mission took place precisely in that region, an area that could provide answers to many questions. Its orbital path passed through zones where, according to calculations, observation windows might be located. These would be periods when the spacecraft was within line of sight, and its cameras could capture important details. But where are these images? Why haven't we seen them? The situation has become even more complicated because the information available to the public is only part of the picture. The story is further complicated by the existence of a so-called third part, a chronology of observations and events related to the Psyche mission. There are moments when the spacecraft was in a position ideally suited for capturing interesting images, and such windows opened more than once. Yet, despite this, public records and reports of what was done often contradict each other or remain completely hidden. It is crucial to understand exactly where these images are located and why no one has managed to find them in open access so far. We have hit a wall of misunderstandings because ground-based and space telescopes disagree about what they saw or could have seen. This creates the impression that the overall picture is finally obscured, and the answers are hidden behind a veil of secrecy. Meanwhile, there is one of the most important topics that has remained outside public discussion so far. These are unofficial, hidden, possibly even very significant observations made by the Psyche spacecraft, which are not disclosed in open sources. Traveling through interplanetary space, this spacecraft carries a set of instruments designed to collect scientific data. Although its main mission is to reach the asteroid named Psyche and study its rich metal surface, it also has additional capabilities. During its flight, even before arriving at the target, the spacecraft regularly performs imaging for system calibration, navigation shots, and conducts extra-planetary scientific observations. These images are taken with special cameras that allow for detailed photographs of the surrounding space. Among the spacecraft's equipment is a thermal imager, a device capable of capturing in the infrared range, enabling the detection of thermal anomalies and the production of highly detailed photos of the asteroid's surface and environment. During cruise, a team of engineers and scientists constantly directs these cameras at various objects to test system performance, calibrate instruments, and, when necessary, gather additional scientific data. This is a standard procedure for interplanetary missions, where the spacecraft, moving along its trajectory, uses every opportunity to collect data. And here is where the most intriguing part begins. These photographs taken by the camera are not only technical material necessary for system testing and calibration. Essentially, they are part of a scientific collection that could open new horizons in our understanding of space. NASA, like most space agencies, publishes some of this data so that the scientific community and enthusiasts can review the results. For example, calibration images are available in the public domain. This situation can have many different explanations, and it is important to exercise caution to avoid jumping to hasty conclusions or making unfounded assumptions. Initially, it is best to consider the simplest and most harmless versions of what is happening, as they are quite logical and could easily explain the current circumstances. Data transmission from spacecraft is a complex and limited resource, crucial for the successful completion of the mission. In deep space, each communication window with Earth represents a restricted period during which the spacecraft can send accumulated data. Mission planners carefully prioritize which data to transmit first and which to defer. The primary focus is on engineering telemetry parameters necessary for monitoring and diagnosing the spacecraft's condition. After that, scientific data related to the mission's main objectives are transmitted, followed by everything else. For example, if the Psyche cameras captured images showing the Atlas, these frames might be stored within the spacecraft's memory and scheduled for transmission during the next communication window, provided there is sufficient bandwidth. It is important to consider that the data transmission process includes not only sending the data but also compressing it and managing the volume of information. Spacecraft do not have unlimited memory capacity, they use so-called circular buffers. These devices operate on a cyclic recording principle. New data overwrites old data if it has not yet been transmitted. As a result, if the Atlas images were not marked as priority, they could have been heavily compressed or even completely overwritten by later data obtained during other observations. This mechanism works much more frequently than society often assumes and, unfortunately, often results in not all full-resolution frames reaching Earth. Additionally, there may be situations related to errors in metadata or incorrect indexing. Even if the images exist within the archive, they could be miscatalogued or mislabeled. For example, timestamps might be incorrect, target fields improperly marked, or headers damaged. People who have worked with large astronomical databases and archives are well aware of how easily important information can be lost or misplaced simply because files are stored in the wrong folders or labeled with incorrect keywords and tags. As a result, an image of the Atlas could have ended up in an archive under a name indicating, for example, a calibration frame or a starfield shot, waiting for someone to notice a truly significant object or event within it. Bureaucratic reasons cannot be ruled out either, which might explain delays or the lack of public access to certain data. Space agencies often have specific embargo periods, time restrictions on publishing information established by data rights policies or internal regulations. Mission teams frequently have exclusive access windows to the collected data, allowing engineers and scientists to thoroughly analyze the results before they are made available to the public. It is possible that the images in question are temporarily kept within the team's possession, with their publication scheduled for a later date, until a certain stage of processing and analysis is completed. In such cases, scientific groups are given the opportunity to be the first to examine the results, which is important for protecting the interests of those who developed and calibrated the instruments, as well as for ensuring they can publish their findings before others gain access. All these explanations seem reasonable and logical, without implying any complex conspiracy theories or hidden information. These are quite ordinary, if I may say so, technical and administrative issues that arise during the course of complex, multi-stage space missions. However, an important question arises. The lack of direct evidence of what was recorded or hidden does not mean such evidence does not exist. We cannot know for certain what exactly was captured. Under the Freedom of Information Act, any requests related to obtaining data from government agencies may require the disclosure of various types of information held by government institutions. In particular, one can submit a request to access archival materials stored in government archives and databases. Such materials include mission logs, observation records from the SLU system, as well as reports prepared based on the results of various instruments and devices used in space research. These documents exist and are held by the relevant agencies, and they can quite legitimately be requested by interested parties. An important question is whether among these materials there are images that could shed light on the mystery surrounding the object known as ATLAS. Perhaps these visual data are somewhere in archives, waiting for their moment to be published and made available to the public. Then we might have a chance to see what this mysterious object actually looks like, which could significantly alter our understanding of it. However, another question arises. Do these images even exist? Or perhaps they were never recorded during observations because there was simply no opportunity or intention to do so? And if such footage was captured, why has it not yet been published or made accessible for analysis? Maybe they are held by those who, for some reason, keep them secret, or perhaps, for other reasons, they were never found or preserved in archives. There are several possible scenarios, each opening different horizons for interpretation. If these images do exist and are eventually published, we may finally see the true appearance of the ATLAS object. This, in turn, could help resolve contradictions between data obtained from the TESS Space Telescope and observations made with other instruments, such as the JWST telescope and other astronomical devices. Otherwise, if the images do not exist, we will have to understand why the spacecraft with functioning cameras did not record the most important event that could have become one of the main discoveries in astronomy over the past decade. And if the images do exist but are not accessible, then we are dealing with more serious issues related to transparency of processes and data management in space research. This raises questions about the openness and responsibility of the organizations involved in transmitting and storing observational data about space. It is also worth considering hypotheses related to possible alternative explanations of the object's nature, which may not align with the classical concept of a comet, and theories that attempt to explain the observed data through various hypotheses. In this case, it is necessary to move away from archival questions and turn to more fundamental reflections. Namely, what if the TESS is not a typical comet in the traditional sense? What if we initially misclassified this object, trying to categorize it as a comet or asteroid because it possesses characteristics that do not fit conventional frameworks? Then the question arises, if this object does not follow the rules and laws that usually govern comet behavior, what could it actually be? What alternative scenarios for explaining its nature would meet all our requirements and constraints while also accounting for the observed phenomena? The most discussed hypothesis is the assumption that TESS is a large inert body with microgas emission. Imagine it as a piece of rock and ice formed outside our solar system, under conditions significantly different from those that existed during the formation of planets and comets in our own system. It may primarily be a very stable and inert object that does not actively sublimate like typical comets, yet it releases a small amount of gas through cracks or sparse surface areas where the ice still sublimates. This mechanism could explain the gas signatures detected by scientists using the JWST telescope without the need to assume the presence of a bright and dense dust cloud. Picture a scene resembling a school of fish or a flock of birds moving as a single organism. This is not just a random gathering of individual creatures but a coordinated group where each participant plays its role within a collective whole. Similarly, if we consider the mysterious object of our interest, it can be envisioned as a collection of many small fragments emitting a small amount of gas or dust into the surrounding space. These particles remain within a kind of swarm, not dispersing in different directions, as if connected by invisible threads. Such an image could explain the pinpoint nature of the observed effects. If these fragments are located close enough to each other, closer than our instrument's angular resolution allows, we would perceive them as a single continuous structure. The gas emanating from this swarm would originate from numerous small surfaces rather than a single core, which could lead to completely different scattering properties than those expected from a bright, powerful nucleus. In this case, the scattering effect would be more uniform and complex than in the classical model of a bright tail. However, this model also has its weaknesses. Why do the individual fragments remain connected and not fly apart in all directions? They would need some form of collective gravitational attraction to keep them close together. Without such attraction, in the vacuum of space, these particles would inevitably drift apart over vast distances, turning into scattered debris. Additionally, if the swarm truly represents a collection of similar elements, it should exhibit certain structural changes, stretching, contracting, becoming blurry or elongated, even if individual fragments cannot be distinguished. This creates a coherent picture. Even if we cannot identify separate particles, we still observe some internal dynamics within this formation. Now, let's move to the third, more exotic hypothesis, related to effects occurring at the micro level, at the level of electrons and atoms. This is where the most interesting and astonishing phenomena begin. Suppose that around this mysterious object, for example around Atlas, there are dust particles carrying an electric charge. At the same time, there exists a magnetic or electric field strong enough to hold these dust particles close to the central core. In such a case, the charged dust could levitate or be captured in special configurations, not following the usual ballistic trajectories, but obeying electromagnetic forces. This phenomenon is well known from observations in planetary rings, where dust particles are held by magnetic and electromagnetic fields, as well as in laboratory plasma experiments and in regions where electromagnetic forces dominate over gravity. If Atlas possessed some charge and generated electromagnetic fields through processes that are still unknown to us, then the dust around it might not form a tail at all or could remain confined in a limited area, floating and circulating around the core. As a result, gas composed of molecules is more difficult to hold with electromagnetic forces, and it would still dissipate, but the dust would stay in place, remaining invisible to our optical telescopes that search for extended, luminous structures. Such an explanation could fully account for almost all observed features: a compact appearance, the presence of gas, and the simultaneous absence of a visible tail. However, this hypothesis also has its serious difficulties. First and foremost, how can an inert body, lacking internal activity, generate such strong electromagnetic fields? This requires an energy source, an active generating device, which raises additional questions. And this is precisely what leads us to the fourth, most controversial hypothesis, a hypothesis that, despite its strangeness, cannot be dismissed. We have a number of unusual phenomena, observations, and signs that cause some surprise and caution among scientists. However, it is important to emphasize that these facts alone are not convincing evidence of something unusual or artificial. Each existing hypothesis formulates its own predictions, which allow us to suggest possible scenarios of development or characteristics of the studied object. For example, the micro-ejection hypothesis suggests that ultimately we should observe a certain dust accumulation, which would be relatively weak but detectable with careful and prolonged observation. This effect should manifest as a small but stable formation of particles, which, despite their unremarkable appearance, would become visible with sufficient observational detail. In another model, based on the concept of a fragmentary cloud, it is predicted that over time, as the object swarm develops, it should undergo structural changes. These changes may manifest in transformations of shape, material distribution, or other characteristics related to the system's dynamics. The electromagnetic model, in turn, suggests that we must necessarily detect certain signatures of electromagnetic fields, characteristic anomalies in radio wave polarization, and possibly radio signals emanating from the object. These signals could serve as indicators of artificial sources or structures generating electromagnetic radiation. Within the framework of the hypothesis of artificial origin, phenomena that cannot be explained by natural processes are predicted. These may include unusual geometric shapes, spectral lines associated with industrial or technological structures, as well as temporal patterns indicating the presence of controlled processes rather than chaotic natural phenomena. What is particularly interesting is that none of these models can perfectly account for the entire spectrum of observed facts. Each hypothesis explains certain aspects of the data while simultaneously raising new questions and doubts about other characteristics of the object. Natural explanations often require assumptions about highly improbable combinations and configurations to account for all the findings. Exotic hypotheses, which suggest natural processes previously unobserved under similar conditions, demand physics that extends beyond currently known laws and models applicable to comets and other celestial bodies. Finally, the hypothesis of artificial origin proposes recognizing that we are dealing with technology from an alien civilization. This is a step that most scientists are unlikely to take without irrefutable and convincing evidence. However, sooner or later, we will have to choose which of these explanations is most probable or accept that we may be encountering something beyond conventional concepts. After all, the standard model of comet behavior is what we have come to consider the truth: that these objects are natural celestial bodies governed by the laws of physics. But the situation is such that this approach is beginning to fail, as the object continually demonstrates behavior that is uncharacteristic for it. If the object consistently defies our expectations and does not fit within the framework of familiar models, then sooner or later, it becomes necessary to reconsider and update our understanding of its nature. Perhaps we are already at a stage where our current models do not allow us to interpret it correctly. This is evidenced, for example, by the case of the object named Atlas. We may be at the point where it is time to determine what exactly in its nature is unnatural and requires explanation. The next important task is to formalize the problem, that is, to clearly define what would convincingly prove the unnaturalness of this object. An analogy can be drawn, like drawing a line in the sand to clearly mark the boundary between natural and artificial. This highlights the need to establish specific, verifiable criteria that even skeptical scientists cannot ignore or refute. The first such criterion is the presence of a structure that cannot exist according to our known laws of physics. If we had the ability to take a high-resolution image of an object to discern its shape, or if spectroscopic studies in space revealed traces of elements or compounds that exist solely as a result of nuclear reactions, or if we encountered industrial substances, synthetic polymers, or isotopic ratios not found in nature, it would serve as a troubling and alarming signal for scientists and researchers. Such findings would indicate the artificial origin of these objects or processes, raising serious questions and requiring in-depth analysis. The entire universe produces a limited set of chemical substances formed through stellar nucleosynthesis and natural chemistry occurring in space. Anything beyond this natural repertoire demands special attention and confirmation, as it could be a sign of anomalous processes or even evidence of extraterrestrial activity. The third crucial criterion for evaluating unusual objects or phenomena is the detection of anomalies through multi-band registration. This involves capturing images in various electromagnetic wave ranges, overlaying the resulting images, and analyzing them carefully. Natural objects, even the most unusual, exhibit patterns predictable by physics and astronomy. For example, hot regions in space emit more infrared light because their temperatures are higher, and dust present in interstellar space scatters optical light, making these areas less transparent. Gas clouds emit light at specific wavelengths related to their chemical composition and conditions. However, if, by comparing images taken in different wave ranges, we find discrepancies that cannot be explained by physical laws or common processes, this would indicate the presence of something more complex and unusual than simple thermal radiation or light scattering. For instance, if a structure appears in one range but is absent in others, it could point to unknown or artificial sources of radiation rather than natural processes. The fourth important criterion is the verification of metadata and telemetry signatures. That is, all information related to the origin and processing of data. In the case of observations from spacecraft, raw frames should be accompanied by precise timestamps, instrument settings, checksums, and calibration data. These metadata allow for verifying the integrity and authenticity of the information, comparing it with mission logs recorded in official documents. Discrepancies in these data may indicate possible distortions or even intentional falsification. More importantly, the presence of consistent, fully verifiable metadata significantly strengthens confidence in the conclusions drawn and the observational results. Otherwise, proving something truly extraordinary becomes nearly impossible, because the authenticity and accuracy of the original data are the foundation of any scientific claim. The fifth criterion is the presence of correlated signals across different physical domains. Imagine a situation where an object or phenomenon simultaneously exhibits optical illumination, radio bursts, X-ray emissions, and even neutrino signals, all recorded at the same moment in time and linked to the same events. Such a comprehensive set of data would be exceptional and highly valuable for scientists. Natural cosmic processes, such as stars, blazars, or supernovae, can produce multi-wavelength radiation, but their signatures follow well-established patterns, thoroughly studied and confirmed by numerous observations. However, if something fundamentally new is observed that does not fit existing models and causes unusual correlations across different wavebands, it would require a new explanation. For example, if signals were detected that simultaneously manifest in optical, radio, X-ray, and neutrino ranges, and all these manifestations are interconnected according to specific patterns, it would indicate the presence of unusual sources or processes surpassing our current understanding. The history of science is rich with examples. Sometimes, in scientific research, there is a need to keep certain information secret, especially if its disclosure could have strategic or national significance. In such cases, some data may be classified or entirely prohibited from publication, and this is often not related to their scientific value or importance for understanding the universe. However, many people and scientists harbor a persistent fear, the fear of becoming a subject of ridicule or being misunderstood. This is especially true for researchers who dare to claim the existence of extraterrestrial civilizations or cosmic objects without having 100% proof of their hypotheses. In such situations, the risk of public condemnation or damage to reputation seems particularly high, and it often comes at a great cost, since the professional effort involved in preparing, verifying, and confirming data is complex and expensive. As a result, the question arises: what should be the ideal set of data to be considered as maximally reliable and convincing? The answer is simple: these should be raw, uncompressed, unaltered original frames that retain all information in their initial form. A complete set of metadata is also necessary. Details about each file, its creation parameters, the equipment used, and the time and place of filming. All of this must be verified by independent sources to exclude the possibility of tampering or errors. An important aspect is checksums, special digital signatures that ensure the data has not been altered or forged since receipt. Moreover, having multiple independent observations made with different instruments and tools is crucial. This helps confirm the authenticity and accuracy of the results. This entire body of information should be accessible to the wider scientific community so that anyone interested can analyze it, verify, reproduce the results, and confirm their validity. Ideally, the entire chain, from data collection to storage and subsequent analysis, should be documented and transparent for verification. Any video, photograph, or public statement related to the hypothesis of the existence of some atlas or other unusual objects must meet these high standards of transparency and reliability. If someone claims to have photographs of a spaceship capturing something unusual, the first question should be: where exactly are the original raw frames? Can the metadata associated with their creation be verified? Will the data owner provide independent experts with access? Without this level of transparency and openness, we remain only witnesses to more blurred and ambiguous evidence, which raises more questions than it answers. After all, to draw convincing conclusions about potential anomalies or unusual phenomena, proof at the highest level is required. The burden of proof in the case of extraordinary claims is not merely a formality but an integral part of the scientific approach. It must be very high. The more unusual the claim, the more rigorous the confirmation of its truth must be. Over the years, science has achieved significant progress precisely due to strict requirements for evidence, reproducibility of results, and transparency of processes. Whenever new hypotheses or observations emerge, the scientific community demands confirmation that can be verified and reproduced by independent researchers. This helps avoid errors, whether accidental or intentional, and ensures the acquisition of objective knowledge. At the same time, scientific minds do not ignore unusual phenomena or anomalies. On the contrary, they study them carefully and take them seriously. They understand that progress is only possible when there is a willingness to revise existing models and hypotheses in light of new data. In this regard, observations related to ATLAS are currently the facts that evoke serious curiosity and require further investigation. They are sufficiently unusual to attract attention but not yet definitive enough to draw final conclusions. The future depends on whether access can be gained to key observations that may fill the existing gaps in our understanding. Long-period transients, or LPTs, represent a relatively new and little-studied category of astronomical objects that exhibit activity in the radio band with a certain regularity, measured in tens of minutes or even hours. These mysterious objects are rare and often fall outside the scope of existing classification systems because their properties and mechanisms of origin have not yet been fully explained. They attract particular interest from astronomers precisely because they do not fit into conventional models and require new approaches to understanding the processes occurring in our universe. The first object in history with recorded pulsations in both the X-ray and radio ranges was an astrophysical source designated ASCAP J1832. Its observations sparked interest in so-called strange and unusual transients, as it demonstrates unique properties, making it truly an extraordinary phenomenon. Precise data on this object indicate that it emits radio bursts lasting about 2 minutes, followed by a quiet period of approximately 42 minutes. Then the burst repeats, forming cycles that on average recur with an hourly regularity. Such a stable and predictable cycle led scientists to consider the presence of a mechanism inside the object responsible for its recurring activity. Further research conducted with the Chandra Space Observatory showed that the X-ray pulses of this source are synchronized with the radio bursts. Although a complete coincidence of their timing characteristics is not observed, there is an obvious correlation, indicating a close connection between the processes generating radiation in both ranges. These observations suggest that the phenomena occurring inside the object are related to the same physical mechanisms that activate both X-ray and radio emissions. Regarding the location of this mysterious source, its position indicates that it is approximately 15,000 light-years from Earth, meaning it is somewhere within our galaxy. However, despite this considerable distance, it is not associated with any prominent stellar association, nebula, or known star cluster. This fact further complicates the task of explaining its nature, as it does not belong to well-studied groups of objects, and its origin and mechanisms of activity remain a mystery. A natural question arises: what could have caused such unusual signals? The first and most obvious suspects are magnetically active objects. Primarily, these are the so-called magnetars, neutron stars with incredibly powerful magnetic fields, which are known to exhibit activity in the form of pulsations and intense bursts. Magnetars can emit pulses in the radio range, however, their pulsation periods are usually associated with very short timescales, from a few milliseconds to several seconds, which is significantly shorter than the observed 44-minute interval. Therefore, explaining the observed 44-minute gap would require inventing some unusual configuration or a new physical model that would allow the magnetic field to slowly accumulate energy and periodically release it with such rare and long intervals. To date, no existing theory fully explains such observations. There is a hypothesis about the existence of ultra-massive white dwarfs, dead stellar cores that have shrunk to the size of Earth after completing their life cycle and continue to rotate, maintaining strong magnetic fields. If such a white dwarf had a very long rotation period, for example, around 44 minutes, and active processes were occurring, such as matter accretion or magnetic reconnection, then it could be assumed that periodic pulses corresponding to the rotational periphery might appear. However, most white dwarfs rotate much faster, and those that rotate more slowly usually have lost their magnetic fields or have significantly weakened activity. Therefore, explaining such a phenomenon with white dwarfs is a different matter altogether, as these phenomena are fundamentally different in nature and occur in entirely different contexts, making their comparison a delicate matter. That is precisely why I want to explain why it is important to consider such cases with particular attention. If in our galaxy a single object appears capable of disrupting existing astronomical patterns, emitting a signal that does not fit into any known class of cosmic bodies and phenomena, we must be very cautious in making claims about what is possible or impossible regarding other similar strange objects. An event like ASCAP J1832 serves as compelling evidence that mysterious mechanisms, tricks, and properties still exist in the universe, which we have yet to catalog, and that there are classes of objects still to be discovered. This discovery also highlights how much we miss by not noticing or understanding. ASCAP is a relatively new network of radio telescopes that only began operation a few years ago. While Chandra has been operating since the 19th century and has accumulated extensive observational experience, it can only record signals that are specifically indicated by the operator. In contrast, ASCAP J1832 likely pulses for thousands, perhaps millions of years, yet we have only recently discovered it. This raises the question: how many other strange objects are hidden from us simply because we have been searching in the wrong places or using the wrong methods? Modern technology allows us to detect many new anomalies if we put in the effort and properly configure our instruments, but often we look in the wrong areas or employ unsuitable techniques. This is crucial for probability models, as new discoveries like ASCAP J1832 alter our initial assumptions. Previously, it was assumed that unusual periodic signals across several ranges were more likely anomalies, not characteristic of natural objects, and any claims of such signals were regarded as errors or instrumental artifacts. Now we know that such signals do exist, although we still lack a clear explanation for their origin. This should prompt us to exercise much greater caution and not dismiss anomalies in other objects simply because they do not fit existing models and theories. Furthermore, this discovery suggests a specific research strategy. If we find one anomaly, we should pay attention to other similar signals and attempt to identify patterns or connections among them. Perhaps there is a common cause behind their appearance, or perhaps not, but without careful analysis, we will never know. This idea leads us to an important question: could seemingly unrelated objects like ATLAS and ASCAP J1832 be connected by some underlying physical principle? It may seem absurd, but before dismissing it, we should at least try to understand. Moving on to the question of cross-connections and the relationship between these objects from the perspective of potential physical theories. Are ASCAP J1832 and ATLAS somehow related? At first glance, there is no evidence for this, as these are objects differing in characteristics, scales, and contexts. Some are individual astronomical phenomena, others are related to specific types of radiation, and what unites them is only the fact that both attract the interest of researchers. However, in our analysis, we can look for hypothetical analogies and consider whether there are potential mechanisms capable of acting in both cases. Perhaps the same exotic physics operates in different regimes, creating similar signals. Even if it ultimately turns out to be unlikely, contemplating this question helps us understand what experiments and tests need to be conducted. Let's begin by examining the energy scales. ASCAP J1832 generates both radio waves and X-ray radiation. The radio emission may result from synchrotron radiation, a process in which charged particles spiral within magnetic fields, or from coherent plasma processes. In the realm of cosmic phenomena, there are processes that evoke truly profound interest among scientists and sometimes even mysteries that remain without a definitive answer. One such process is the interaction of hot plasma, magnetism, and particle acceleration to relativistic speeds, velocities close to the speed of light. These energetic phenomena surpass in intensity everything we typically associate with comets, which are usually just simple combinations of ice and rocks heated by the sun. But what if, inside or near objects like ATLAS, something much more powerful is happening? What if these bodies are capable of sustaining or generating strong magnetic fields that influence their surroundings and produce observable phenomena? Indeed, comets have induced magnetospheres. When the solar wind, a stream of charged particles emanating from the sun, interacts with their ionized comets, a weak interaction occurs, sometimes manifesting as faint magnetic fields. These fields are not organized into complex structures characteristic of planetary magnetospheres or accretion systems around stellar objects, but they do exist. So the question arises: What if ATLAS has not only an internal magnetic field of extraordinary strength but also the ability to carry or generate charged particles that form complex magnetic structures? Could such conditions create mechanisms leading to radio emission? Plasma physics offers several possibilities for this. One such mechanism is coherent radio emission, which can occur under certain conditions due to plasma instabilities. For example, in regions where the density of charged particles changes sharply, or in boundary layers where different types of plasma collide, conditions become favorable for generating radio pulses. If ATLAS emits gas that is then ionized by the sun's ultraviolet radiation, the resulting ionized coma is a plasma capable of supporting waves, instabilities, and emission mechanisms. In most cases, such processes under normal conditions are too weak to be detected or observed with current instruments. However, under special circumstances, for instance, at extreme charge densities, unusual magnetic configurations, or strong local disturbances, signals can become sufficiently intense and noticeable. In this context, it is interesting to compare with an object known as ACEPJ1832, which exhibits pulses approximately every 44 minutes with precise regularity. This pattern suggests the existence of rotational movements, orbital oscillations, or resonance processes that cause periodic bursts of activity. However, when examining ATLAS, its optical observations do not show such regular behavior on similar timescales. If there are signs of periodic activity, they manifest over intervals of days or even weeks, rather than minutes. This implies that any proposed mechanism responsible for these signals would need to operate across a wide range of timescales. Such a scenario seems unlikely unless we assume the existence of a common underlying process that can scale differently in various environments and conditions. Regarding X-ray emission, its presence in comets has been documented previously. This radiation results from the process of ion recharging of solar wind ions interacting with neutral atoms in the coma. It is relatively weak and requires highly sensitive instruments to detect, but it is entirely plausible. If ATLAS's coma becomes unusually dense or active, X-ray emission would become a quite expected phenomenon. An important question is whether this emission would have a periodic nature, structured and synchronized with any observable signs. In most cases, charge exchange between the object and its environment occurs fairly evenly, without sharp impulses. Therefore, if we were to hypothesize a scenario, it could involve the idea that within interstellar space, when considering smaller objects like ATLAS, the physical processes related to plasma behavior and electromagnetic fields preserve their fundamental laws and principles. However, they manifest in a completely different form compared to larger celestial bodies. In such cases, we encounter small-scale plasma clumps, unusual ratios of gas to dust, and possibly radio bursts that are so weak or short-lived that they are nearly impossible to detect with current instruments. This hypothesis allows us to make specific, testable predictions based on theoretical models. If we assume that the objects ATLAS and ASCAP J1832 operate according to common physical principles, then our efforts should be grounded in a reliable foundation. We should look for faint radio pulses originating specifically from ATLAS, especially during its perihelion, when it is closest to the Sun. During these times, interactions with the solar wind are at their most intense, and any activity manifestations could become more noticeable. In turn, X-ray flares, if they occur, should be associated with optical brightening of the object or gas ejections, indicating significant energetic events in its atmosphere. At the same time, it is possible to study the signs of organized magnetic structures manifested in the polarization signatures of scattered light coming from ATLAS. These signatures may indicate the presence of complex magnetic fields organized into specific configurations. Another important aspect is Faraday rotation, the effect in which the polarization of radio emission changes as it passes through a magnetic field. Observing this rotation in signals originating from the source can help determine the strength and structure of the magnetic fields present near the object. The detection of neutrinos associated with ATLAS or similar objects is also a significant line of research. If particle acceleration mechanisms in such objects are indeed active, they could produce high-energy particles, including neutrinos, which in turn could be detected by observatories. However, it is important to emphasize that most of these potential observations have either not been conducted or not been publicly published. Radio telescopes have not carried out systematic, high-time resolution monitoring of ATLAS, and X-ray observatories were likely not pointed at it during its active phases when such signals might be most detectable. Consequently, to date, we either lack or do not have access to reliable data confirming or refuting the presence of associated activity. This means that further research requires a systematic approach. If, next time, we observe ATLAS in the radio band during its active periods and find no signals that constrain existing models, this will be a valuable result. Such an outcome would indicate that there is no coherent plasma or synchrotron emission, nor mechanisms capable of generating radio waves under these conditions. This would rule out a range of theories and hypotheses that assume such phenomena. On the other hand, if during observations we detect radio pulses, correlations with X-ray emission, or any other signatures predicted by theoretical models, it would be truly extraordinary. Such a result would suggest that ATLAS behaves outside the usual framework of cometary activity. It demonstrates activity associated with phenomena typical of active stellar objects like ASCAP J1832. This opens the door to a new, exotic realm of astronomical research, where conventional explanations no longer suffice, and we will need to consider more complex and unusual mechanisms than those we are accustomed to. The key is to maintain a systematic and consistent approach. Anomalies recorded in one object provide important clues for interpreting similar phenomena in other cases. Patterns are revealed precisely through this. Allow me to explain in detail and uncover the meaning of this astonishing phenomenon, as the numbers and scales involved often lose their intuitive clarity, turning into abstract figures that are difficult to grasp on a common perceptual level. All of this magnitude is nothing more than 1 billion electron volts, a scale that far exceeds our usual measurements by many times. For comparison, protons accelerated in the world's largest particle accelerator, the Large Hadron Collider, reach energies of about 14 trillion electron volts. Meanwhile, the object in question is a neutrino, which carries energy exceeding that of these protons by 16,000 times. It's like a cosmic projectile launched from sources beyond human comprehension, so powerful that modern science still lacks a complete theory to explain how it happens. In this sense, neutrinos are ghost particles that pass through ordinary matter as if it doesn't exist, ignoring collisions and obstacles. Currently, billions of such particles originating from the Sun pass through your body, through the Earth, and continue into the vastness of space, without interacting with any atoms. They have virtually no mass, no electric charge, and other properties that would allow them to collide with or be trapped by normal matter. Detecting them requires enormous volumes of transparent substances, ice or water, inside which special sensors are placed. These instruments monitor extremely rare cases when a neutrino does interact with matter, causing a charged particle to appear, which, moving faster than the speed of light in that medium, emits characteristic light radiation known as Cherenkov radiation. Modern detectors, such as KNET, use the Mediterranean Sea for this purpose. In these setups, a large amount of water serves both as the medium for neutrino interaction and as its detector. Sensitive light-emitting diodes are arranged along cables submerged in the water, capturing any flashes of radiation characteristic of neutrino interactions with water atoms. These flashes are short-lived and highly specific light signals called Cherenkov flashes. They serve as clues indicating that an interaction between a neutrino and an atom occurred within this volume of water. The component called Archer detected a specific event by recording a unique signal pattern that revealed the neutrino must have had at least 220 electron volts of energy. The analysis of this signal was carried out using complex physical models, and the results confirmed its authenticity. This is not a mistake, a coincidence, or a false alarm from equipment. It is a real fact confirmed by modern science. Why is this important? Because such neutrinos with such enormous energies serve as indirect evidence of the existence and operation of cosmic accelerators functioning on scales that our current science is only beginning to understand. Among the most likely candidates for these natural accelerators are so-called blazars, supermassive black holes located at the centers of distant galaxies. These black holes actively feed on the surrounding matter, forming powerful jets of plasma that move at speeds very close to the speed of light. As a result of these emissions, protons within the jets gain extremely high energies. When these protons collide with surrounding photons or matter, pions are produced, particles that subsequently decay into neutrinos. Besides blazars, there are other possible sources of such high-energy neutrinos. For example, gamma-ray bursts, which are the dying screams of massive stars collapsing into black holes. If we accept as truth that ATLAS contains some exotic, little-understood matter, or possesses properties still unknown to modern scientists, a very logical question arises. Can such an object, located within our solar system, interact with the solar wind or interplanetary medium in such a way that this interaction produces particles of extremely high energy? In other words, is it capable of playing the role of a source or catalyst for processes that lead to the appearance of neutrinos, these mysterious, almost impenetrable particles, through mechanisms that do not operate in typical comets or other known cosmic objects? At first glance, this seems like an absurd hypothesis, especially because we practically do not understand what ATLAS truly is. We call it a comet because it is within our solar system, exhibits some activity, and has characteristics similar to those of comets, but all its properties and behavior raise many questions and seem anomalous. To determine whether there is a connection between the mysterious activity of ATLAS and a possible emission of high-energy neutrinos, there is a specific way to test this. Continuous observations are conducted using specialized detectors such as KM3 IceCube, located at the South Pole, and other similar instruments. These detectors record the arrival of neutrinos, and each detected event is accompanied by an exact timestamp and the direction from which the neutrino arrived. If, during the passage of ATLAS through the perigee, or during its active phases, or when observing any unusual phenomena, whether optical or spectroscopic signs, a burst of high-energy neutrinos were to occur, then by comparing the temporal and spatial parameters, a correlation could be established. Such a correlation, if sufficiently significant, would indicate a physical connection, meaning that ATLAS, despite its mysterious nature, is somehow related to the processes producing neutrinos. Similar analytical methods have been used in the past when scientists searched for links between various astrophysical phenomena and the signals they detected. For example, when IceCube detectors recorded a neutrino coming from the direction of a well-known blazar during its active phase, it confirmed that such objects are indeed sources of neutrinos. Overall, the revolution in multi-messenger astronomy and astrophysics is based precisely on the ability to correlate signals of different types, light, neutrinos, gravitational waves, and find relationships between them. Each of these signals tells a unique story about the source, since they are generated differently and propagate through space according to different laws. Neutrinos are of particular importance in studying such processes. These particles are unusual because they are very difficult to block or absorb. If ATLAS is truly capable of producing neutrinos, they would escape from its interior directly into space, carrying valuable information about the processes that generate them. Unlike gamma rays, which can be absorbed by gases or dust in interstellar clouds, or radio waves, which can scatter and distort as they pass through the interplanetary medium, neutrinos pass through all these obstacles almost without distortion. They can reach Earth with almost no loss, pointing precisely to their source, making them the best cosmic messengers for studying phenomena that would otherwise remain inaccessible or opaque to us. The detection of neutrinos with an energy of around 220 electron volts, for example, by a modern detector such as Peter, serves as compelling evidence that such messengers exist and that processes powerful and intense enough to produce such particles are occurring in the universe. This is an important reminder that our picture of cosmic phenomena is still far from complete. We still do not know all the ways in which nature can accelerate particles, create, and generate more mysteries. The increasing number of enigmatic cosmic phenomena continues to surprise scientists and expand the horizons of our understanding of the universe. It is quite possible that ATLAS is merely a comet with an unusual composition, and we tend to exaggerate its significance, attributing to its special importance. However, it is also possible that this will become yet another entry in the long list of strange phenomena that we previously did not anticipate and about which we had no suspicion of their existence. Another similar event, for which either new physics or the introduction of entirely new categories and concepts will be required to fully understand its nature, is observed. The only way to make sense of this is to continue monitoring such phenomena, compare data, look for correlations, and ask ourselves, could these anomalies have a common origin or explanation? To find answers to these questions, access to the entire dataset is necessary, including information that may be stored in observation archives and waiting for analysis. In particular, this concerns the so-called ninth part, the overlay of data related to space weather. In this context, coronal mass ejections, forecasts of auroras, and the importance of studying the environment as a whole become especially significant. While we have been focusing our efforts on studying distant cosmic objects and exotic particles from deep space, something much closer and simultaneously much more complex was happening behind our backs. This is solar activity, which has reached extraordinary intensity in recent years. Over a short period of just a few days, 4 powerful coronal mass ejections occurred from the Sun and impacted our planet. These ejections are gigantic clouds of magnetized plasma, billions of tons of which were expelled from the solar corona and are traveling through space at speeds exceeding millions of kilometers per hour. They are expected to reach Earth between October 15 and 17, 1925, causing concern among specialists. When these massive streams of solar matter collide with Earth's magnetic field, they trigger powerful geomagnetic storms, events that can lead to significant changes in our planet's magnetosphere. For observers monitoring the polar lights, this is exciting news, as such intense solar storms contribute to the appearance of bright and widespread auroras near the poles. As a result, the stronger the storm, the farther from the poles one can observe the magnificent light phenomena formed by charged particles interacting with the atmosphere. These 4 coronal ejections, consisting of billions of tons of charged plasma moving at incredible speeds, prompted forecasts of especially bright and large-scale auroras, which could even be visible at mid-latitudes. This event is particularly interesting for astronomers and specialists engaged in observing faint and rare cosmic light, as space weather is becoming one of the most serious and unpredictable factors hindering their work. The same charged particles that create the stunning and mesmerizing display of the northern lights also generate numerous noises and interferences. Radio observations used to study space begin to distort and are affected by ionospheric scintillations, oscillations in the ionized layers of the atmosphere caused by solar storms. These fluctuations cause signals to flicker and fade, similar to star twinkling, but much more intense and problematic for scientists. During periods of strong cosmic storms, the number of false signals detected by radio telescopes increases dramatically, complicating the collection of accurate data and requiring additional efforts to filter out noise. Moreover, atmospheric luminescence, which occurs when air molecules are excited by solar particles, adds background noise to the images and makes data processing more difficult. This is especially critical for spacecraft, whose instruments are in space, and it is precisely at these moments that the true cunning and trickery, hidden behind apparent simplicity, begin. Space weather, this unpredictable and constantly changing environment, creates the illusion of absolute reliability and plausibility in explanations related to data loss or distortion. It can serve as a very convincing excuse because if important frames are missing from archives, if images contain unexpected artifacts or noise, or if telemetry shows gaps or failures, there is always an opportunity to attribute it to solar storms, solar flares, or other manifestations of space weather. It was during such times that massive coronal mass ejections occurred, powerful events triggered by solar energetic particles, which literally wreak havoc on sensitive instruments. Such ejections can affect a wide range of data, compromise their integrity, and lead to data loss. As a result, the spacecraft, subjected to this turbulent activity, had to switch to safe mode, an operational state in which systems are shut down or enter a special mode to minimize the risk of damage. All these phenomena, predictable and quite explainable consequences that do indeed occur in reality, can nevertheless serve as very convenient pretexts or justifications when problems with data arise. They allow specialists and researchers to divert the conversation and avoid more complex or uncomfortable questions. The problem is that sometimes it is very difficult to determine exactly what caused the malfunctions or data loss, whether they are the result of space weather influences or other factors. Therefore, it is important to pay close attention to details and nuances. The effects of space weather leave behind characteristic signs, unique traces that can be recognized and analyzed. For example, the impact of cosmic rays on sensors manifests as sharp peaks and sudden brightness jumps in individual pixels or small groups of image elements, so-called sharp spikes, which stand out clearly against the rest of the image. Ionospheric flickering, caused by solar storms, is characterized by specific timescales and frequency dependencies. It can appear as periodic oscillations repeating at predictable intervals or as chaotic bursts that cause distortions in telemetry. Additionally, spacecraft and their systems, especially when switching to safe mode, generate characteristic telemetry patterns and event log entries. These patterns help specialists understand exactly what happened, which processes were initiated, and how systems responded to external influences. If researchers have access to all metadata, full archives, system status information, instrument operation reports, as well as calibration records before and after unusual events, they can usually determine the cause of the incident. However, problems arise when such metadata are unavailable, incomplete, or entirely missing. When only information about data loss or damage caused by space weather is provided, and detailed logs, diagnostic reports, or calibration records are inaccessible, it becomes extremely difficult to draw definitive conclusions. In such cases, it is impossible to verify whether space weather was truly the cause of data loss or damage. This can indeed be the case, and such situations do occur. But often, these explanations are merely simplified or shortened versions of more complex processes. Sometimes, the issue may be entirely unrelated to space or solar activity. And this is not paranoia, it's the principle of data integrity and reliability in action. In scientific research, it is crucial to have verifiable evidence, otherwise, any conclusions remain questionable. To achieve this, one must know the exact origin of the data, its path, and processing at every stage. The reliability of scientific findings largely depends on how transparent and traceable the information chain is. When gaps appear in this chain, or explanations become vague, it raises doubts. When observing cosmic phenomena with various instruments, it often turns out that the results obtained from each differ from one another. These discrepancies can raise questions about how much they are caused by actual physical differences in what each instrument records and how much these differences are influenced by technical, environmental, or other effects. This is especially relevant in a situation where, this week, we are hit by 4 solar flares, coronal mass ejections, CMEs, each adding its own complexities to data interpretation. Under such conditions, any observations made during this period must take into account not only the increased background level caused by solar activity but also potential distortions related to the instrument's performance, as well as the heightened uncertainty resulting from the need to calibrate sensors. These factors do not render observations useless, however, they significantly complicate their analysis, and the growing errors mean we can less confidently assess the exact processes occurring with the object under study. For example, the ATLAS spacecraft. In this context, I am particularly concerned about the timing of data publication. If there are sufficiently convincing observational results of ATLAS obtained from spacecraft, and if there are images or measurements capable of clarifying the contradictions we discuss, then why have these materials not been published within a week? After all, during this period, space weather provides us with a clear explanation for possible delays or errors in the data. It would be logical and honest to state, we intended to publish the results earlier, but difficulties arose due to coronal mass ejections, which complicated data processing. The absence of such an explanation is somewhat surprising, although it does not necessarily indicate significant errors or concealment of information. Overall, space weather becomes part of what is called structural blindness, which we face when trying to understand phenomena occurring in space. The environment surrounding us, between us and the object under study, between the instrument and the data archive, between the observation itself and the publication process, creates numerous obstacles, noise, and uncertainties. Some of these barriers are unavoidable laws of physics, such as limitations related to signal propagation and instrument sensitivity. Others stem from technological constraints, like the sensitivity and resolution of detectors, as well as organizational and procedural aspects related to data processing, storage, and dissemination. These organizational processes are often managed by separate entities with their own priorities and limitations, which frequently complicate timely information exchange and transparency of actions. To overcome this so-called blindness and improve the quality of our knowledge about space, it is necessary to use redundancy, that is, to have multiple tools and observation methods, as well as to apply diverse analysis strategies to the same data. An important aspect is the development of transparency. It is necessary to clearly inform what exactly was recorded, when, how data quality control is carried out, and how the processing pipelines are organized. It is also crucial to foster a culture where asking questions about the origin and reliability of data is not perceived as distrust or criticism, but as a natural and essential step in scientific activity that ensures its quality and reliability. Now, let's consider how structurally blind we are in our observational process. Let's take a closer look at what happens in the chain connecting the moment when a photon, traveling through space, reaches the detector, and when we finally gain access to the processed data. This complex pipeline, often invisible and filled with technical details, determines what information about the universe we can realistically obtain. Within it, there are always many points where information can be lost, distorted, or never reach the researchers at all. Let's start with the very basics, the detector. When a photon, triggered by an event on the sun, reaches the sensor, it transfers its energy, creating a signal. This signal, very weak and highly vulnerable, is then converted into digital form. Cosmic rays and charged particles constantly hitting the sensitive elements of space sensors generate various false signals on their surfaces, which must be identified and eliminated in a timely manner. These interferences arise from interactions with orbital conditions and can manifest as random brightness spikes or other distortions in images, making it difficult to obtain clean and reliable data. Specifically, such interferences include hot pixels, areas of the sensor that are constantly in a hot state and do not change their signals, dead pixels, completely non-functional regions, as well as failures and defects in individual columns of the sensor matrix. All these defects and anomalies create characteristic patterns and regularities in the data that are not related to real astronomical objects or phenomena, and therefore require careful filtering and correction. Next comes the data processing stage related to compression. Raw images obtained from space detectors often have very large volumes. For example, a high-resolution image can occupy several hundred megabytes of memory, which becomes a problem for transmission and storage at such volumes. During the observation campaign, which can last several months or even years, the spacecraft can generate thousands of such frames, creating an enormous amount of information. Transmitting all this data to Earth in an uncompressed form is practically impossible due to bandwidth limitations of communication channels. Therefore, data compression becomes necessary. Data compression can be of two types, lossless and lossy. In the first case, all original information is preserved, and after decompression, the data remains completely identical to the original. In the second case, some loss of details is allowed, considering them less important for scientific purposes, in order to reduce the volume. The choice of compression method and degree of compression directly affects the quality and completeness of subsequent analysis, since some details may be lost, which in turn limits the possibilities for further research and interpretation of the obtained data. Another important issue is the limited onboard memory of the spacecraft, known as a ring buffer. In space conditions, the available memory capacity is limited, and the spacecraft cannot store all received data indefinitely. Data are written to memory and stored there until they can be transmitted to Earth or until it is time to overwrite them. If, at the moment of recording, an event of scientific interest occurs but is not marked as a priority, these frames risk simply disappearing, being overwritten and lost forever. Moreover, if the communication window closes before the data are transmitted, there is a risk that these frames will remain unsent, lost from memory, as they will be overwritten by new data. As a result, the loss of important information becomes a real threat, significantly complicating the planning of scientific observations and the collection of a complete dataset. Equally important is the organization of the downlink, that is, the process of transmitting data from the spacecraft to Earth. In space missions, time for data transmission is a very valuable resource and cannot be wasted thoughtlessly. Every spacecraft and mission compete for communication windows, which open at specific times. When the spacecraft comes into contact, it transmits the accumulated data according to the priorities set by the Mission Control Center. First, the telemetry status is checked, information about the operational condition of all spacecraft systems. Then, primary scientific data are transmitted, followed by secondary data, calibration frames, and additional observations if available. The order of transmission is determined by the mission's tasks and current priorities, and any less important information may wait its turn, sometimes for weeks or even months. When the data successfully reach Earth, they enter an archival pipeline where significant processing is required. Unprocessed frames are converted into standard formats to facilitate storage and search. Metadata are included in the headers: observation target coordinates, time of observation, exposure duration, filter settings. Next, two important aspects related to the storage and access of astronomical data are considered: embargo periods and ownership rights to the collected information. In the context of scientific missions, a team of researchers often gains exclusive access to their data for an extended period, often months or even years, before the information becomes publicly available. This approach serves as an important safeguard for scientists who have developed specialized instruments, meticulously planned observations, and invested considerable effort to obtain valuable results. It allows experts to analyze the collected data in a calm environment, prepare publications, and present their discoveries before they are accessible to other researchers and the global scientific community as a whole. This is a reasonable and justified policy that encourages research development and protects the intellectual work of authors. However, this mechanism also introduces a potential problem. A significant portion of interesting and meaningful data may remain locked in closed archives, accessible only to a select few specialists or narrow groups, and thus remain unavailable to the wider public. As a result, there is a risk that crucial information capable of shedding light on the mysteries of the universe simply does not enter the general flow of information, and its verification and reanalysis are postponed. Moreover, bureaucratic barriers and administrative formalities often exacerbate the issue. To publish the data, considerable resources and effort are required. First, files must be prepared, processed, standardized, and accompanied by documentation to help other scientists understand and utilize the information. Additionally, the quality of the data must be carefully verified, ensuring that they are error-free, that observations were conducted correctly and without distortion. Equally important is setting up access and publication systems, which demand time and specialized knowledge. The harsh reality is that space agencies and observatories often face staffing shortages or are overwhelmed with current tasks. As a result, data publication schedules are frequently delayed or canceled. This is especially true for low-priority observations, which often remain in internal archives because scientists lack the time or resources for proper processing and publication. Nevertheless, history provides many examples where, years or even decades after data collection, crucial information was retrieved from archives. For instance, reanalysis of images taken by the Hubble Space Telescope led to the discovery of objects that had been missed during initial processing, sometimes due to limitations of methods or technology at the time. Similarly, the archives of the Voyager spacecraft contain records that were considered lost or inaccessible for many years. Moreover, amateur astronomers, often not associated with major scientific projects, have identified comets, asteroids, and other objects on published images that professionals have overlooked for various reasons. This fact demonstrates that archives are vast and filled with an endless number of frames, and no single specialist is capable of systematically studying every image and observation made over decades. This structural blindness, the inability to see the whole picture, affects all modern astronomy, not just individual projects or missions. Discovering new objects, identifying rare phenomena, and understanding cosmic processes often depend on chance discoveries or re-examining archival data. As a result, we can only observe the part of the universe that has somehow passed through a chain of observations, successfully transmitted to Earth, properly archived, labeled, and analyzed by those with both the interest and resources. It is through this complex and multi-stage channel that we gain access to cosmic information. The true nature of the universe, its deepest and most mysterious aspects, is often filtered through this process, and we cannot precisely know what we are missing. Regarding the ATLAS project specifically, this implies several important points. First, discrepancies and inconsistencies between results obtained with different instruments or observation methods may be partly related to these factors. Third, it is crucial to emphasize that there is a particular strategy that can significantly increase the chances of successful investigation and understanding of the enigmatic object known as ATLAS, as well as other similar anomalies that attract scientific interest. This strategy involves not limiting oneself to a superficial analysis of published results or official reports, which are often compiled and released by institutions. Instead, it is important to delve into archival materials and sources, often beyond standard databases. If possible, raw observation frames should be downloaded, if available, and reprocessed using different assumptions and analysis algorithms. This approach allows for the detection of details that may have been missed during initial data processing or hidden behind noise and artifacts. Special attention should be paid to discrepancies in metadata, for example, dates, timestamps, coordinates, or other attributes that could indicate mislabeling or errors in observation records. These inconsistencies can be key to uncovering hidden or misinterpreted data. To do this, it is necessary not only to cross-check observation logs with archival data but also to conduct a thorough analysis for discrepancies and errors. Such an approach helps determine whether mistakes occurred during report compilation or if there were distortions in the original data. Requests for access to files, coordinates, and FOAS, file of archived signals, files encourage institutions to become more open and transparent. Civil science plays an important role in this process. The participation of amateur astronomers and data processing specialists, who are not bound by institutional restrictions, can become a powerful tool for exploring new approaches and solutions. The unprecedented opportunity to share data, methods, and results allows communities to collaborate, combining efforts in the fight against information secrecy. The history of astronomy is rich with examples of significant contributions from amateurs, private researchers who, with the help of modern technologies and digital tools, can make discoveries alongside professionals. In the digital age, this becomes even easier. Access to archives, software tools, and communities enables anyone interested to participate in scientific exploration. Of course, structural blindness caused by bureaucratic barriers and insufficient data openness remains a real problem. However, it is not insurmountable. Overcoming it requires persistence, technical skills, and a willingness to fight bureaucratic obstacles patiently and for a long time. One of the key conditions for success is the creation of coalitions, groups of people sufficiently interested in obtaining answers to dedicate time and effort to data archaeology, archival analysis, and systematic study. Only through joint efforts can we ensure that institutions feel the need to improve their information transfer channels, make data publication procedures more transparent, and streamline exchange processes. Ultimately, all these data exist in reality. The photon that reached the detector, the signal recorded by the instrument, the bit of information stored in archives. The question is whether we can gain free and open access to them, examine them under a microscope, and conduct our own analysis. This is not only a scientific issue but also a matter of policy, priorities, and understanding of physics. Moving on to the next stage, searching for data. In this context, it is urgently necessary to carry out a series of forensic activities to collect and systematize all the required information. Today, it is no longer enough to simply make guesses or wait for someone else to provide answers. The time demands concrete steps, actions, and decisions to find the data that can shed light on the ATLAS mystery. This roadmap is intended for those who are determined and ready to follow it consistently. The first step is to precisely define the time windows during which the object known as ATLAS could have been within the view of the Psyche spacecraft. To do this, it is necessary to calculate accurate timestamps according to the International UTC system, indicating when this mysterious object might have been in the observation area. An important aspect is the use of ephemeris data, specifically, the information about the positions and motions of celestial objects. When studying space objects, especially when analyzing data obtained during interplanetary missions, it is necessary to consider numerous factors related to the spacecraft's position and operational modes at various stages of its long journey. First and foremost, it is crucial to identify specific time intervals during which the cameras, part of the Psyche instrument suite, could have been pointed toward the object called ATLAS. These orientations could be associated both with deliberate targeted observations, where the goal was specifically to capture images of this object, and with scheduled observation sessions conducted for other purposes, which, either by chance or as part of a broader monitoring program, might have captured ATLAS in their images. This approach is typical for space missions, as optical systems on spacecraft often take many images not only intentionally but also within wide observation spectra, including optical navigation, calibration procedures, or engineering checks covering certain regions of the sky or the surfaces of planets and asteroids. It is quite possible that ATLAS appeared in these images even when it was not the primary target, since its presence could have been recorded as a side effect or within a broad monitoring program. To more accurately determine the likelihood of detecting ATLAS, an analysis of the so-called observation window, periods from the launch of the Psyche spacecraft to the present, is required, with particular attention to those intervals when ATLAS appeared especially bright or was in an optimal geometric position for observation. In this context, it is important to consider all variables that could influence the object's visibility: its brightness at the time, the distance to the Sun and to the spacecraft, as well as the phase angle, that is, the angle between the Sun, the object, and the observer. Equally significant is the activity level of ATLAS, which could either enhance its brightness or obscure it if the surface or atmosphere of the object changed over time. All these parameters must be taken into account when modeling possible observation conditions to assess how likely it was to record ATLAS in the images. The second important aspect is the technical description of the instruments used to capture these images and collect data. Psyche is equipped with specialized cameras with well-known characteristics: field of view size, sensitivity, spectral sensitivity, operational modes, and other technical parameters. These specifications are published in official mission documents, such as technical reports, instrument descriptions, and project materials available on NASA portals or websites dedicated to specific missions. The technical specifications of image generators include pixel scales, spectral sensitivity ranges, readout noise parameters, typical exposure values, and other parameters necessary for assessing the capabilities of the equipment. Analyzing this data allows us to determine what exactly these instruments can detect and under what conditions, such as the minimum brightness required, the exposure duration needed to obtain a quality image, and the limitations imposed by technical implementation. To estimate the likelihood of successfully detecting ATLAS, calculations of its expected brightness at different times are necessary. This takes into account its distance from the Sun and from Psyche, the phase of illumination, that is, the angle between the sunlight and the object, and possible activity variations that could enhance or diminish its visibility. These parameters help model how bright ATLAS would appear to the camera at a specific moment and compare these values with the sensitivity thresholds specified in the technical documentation. Such analysis enables us to understand whether ATLAS was sufficiently bright and close enough to be captured with maximum informational value. In other words, it is important to establish not only the theoretical possibility of observation but also its practical feasibility, whether it was actually achievable rather than just hypothetically possible. In this context, a faint object entering the broad field of view may still be detectable if the conditions are favorable. Within the systematic analysis of data related to observations of celestial objects and phenomena, specialized indices are used as essential tools for quick and efficient retrieval of necessary information. These indices contain aggregated summary data about each individual observation, significantly simplifying the work of researchers and data processing specialists. The main advantage of such indices is that there is no need to load full images or original files for searching and identification, which greatly reduces the load on computational resources and speeds up the search process. As a result, systematic analysis and data retrieval become faster and more convenient. To automate the search process in archival storage, specialized scripts and programs are employed. They enable searching by file names, titles, and annotations, which often contain keywords and phrases indicating specific categories of information. For example, annotations may mention atlases, interstellar objects, calibration targets, as well as general field observations including precise coordinates of observed objects. The use of automated tools significantly accelerates the filtering process and helps identify necessary files among vast datasets. As tools for working with such data, software libraries like Astropy and planetary data reading systems are widely used. They are capable of handling formats accepted in international archives, such as the TESS, Planetary Data System, format. These libraries not only allow reading and interpreting data but also automate the search across thousands of files, which is especially important when working with large space data archives. Regular expressions, or search patterns, help identify various file naming schemes that may indicate specific objects or observation types. As a result, searches in archival repositories should be as comprehensive as possible, not limited to obvious matches but also considering hidden or less noticeable entries. It is important to note that sometimes the most valuable and interesting data may not be in primary archives but in additional collections or datasets that, for various reasons, have been marked as low quality or excluded from the main dataset. Such materials may contain unique information or unexpected discoveries, so careful attention and thoroughness are required during searches. Both engineering data and calibration frames, as well as excluded observations that may have been mistakenly or due to certain circumstances removed from primary scientific archives, should be checked. When automated search and analysis tools do not yield the desired results, the next step is to submit official data requests. If the needed information is not available in public archives, one should follow the procedures provided by the Freedom of Information Act, FOIA. In such cases, it is crucial to formulate the request clearly and precisely to maximize the chances of obtaining the desired data. For example, one might request all raw image frames captured by a spacecraft camera, such as Psyche, during specific observation windows. In addition to these frames, it is necessary to request accompanying metadata, instrument logs, and quality assessments of the data received. Clarity in the request is vital. Vague or ambiguous wording can lead to delays, incomplete responses, or even the need for further clarification. FOIA responses may be delayed and may contain conditions or requirements for redacting certain data. Common grounds for denial include issues related to national security, confidentiality, or data that, for various reasons, did not undergo standard processing or verification. Even a denial of access provides important information for researchers. It indicates whether such data exists in the archives and the reasons why it is not published. Reaction time and the nature of the refusal or removal from publication can serve as additional indicators of the status and availability of the relevant materials. It is equally important to consider international mechanisms for data retrieval. If organizations or agencies outside the United States are involved in the project, such as the European Space Agency or the Japanese JAXA, they also have their own systems. Although detailed telemetry data are often absent from publicly accessible archives, they still exist and are stored in closed or specialized systems. Access to this data can be obtained by submitting appropriate requests through established communication channels and procedures. When logs show that observation cameras were turned on and their lenses were aimed precisely at the coordinates associated with the ATLAS object, yet no images or videos are found in the archives, a clear contradiction arises that requires thorough investigation. Such discrepancies may indicate various possible reasons: data transmission failures, errors during storage, or a decision to exclude certain observations from the archive for some reason. In each case, the consequences can differ significantly, so appropriate measures should be taken to clarify the situation. First of all, it is important to verify checksums and the change history of files to ensure their integrity and authenticity. Digital files, especially large datasets, are typically accompanied by hash values that confirm their unchanged and intact state. Archives should store these checksums along with metadata about file versions, dates when they were added, modified, or replaced. This metadata plays a crucial role, as it allows verification that the data has not been corrupted or deliberately tampered with, and helps trace the origin of each piece of information. As part of the verification process, logs for relevant periods should be requested and reviewed to identify potential gaps, anomalies, or files with modification dates that do not match the original archiving time. Such analysis helps determine whether data has been altered, deleted, or otherwise processed, which could indicate errors or suspicious activity. Lawful and regular data processing is generally carried out during calibration improvements or error correction procedures. An essential condition is transparency of this process and comprehensive documentation of all changes. To increase confidence in data integrity, checksum comparisons should be made between different mirror copies or archives, if available. Discrepancies between the mirrors are a sign of potential issues with data synchronization or integrity that require further analysis. It is also necessary to compare the file timestamps with the records in the mission event logs to ensure that any changes made to the files correspond to documented actions of processing or updating. This step helps eliminate the possibility of accidental errors or unauthorized interference. Regarding reprocessing, even in the absence of precise atlas frames, available public or archival images from relevant periods can be used. All data related to this time interval must be downloaded and analyzed to identify possible signs of the target object. Modern image processing techniques offer extensive capabilities for detecting information that might have been missed by automatic systems. These methods allow overlaying and stacking images to identify faint signal sources invisible during normal viewing. It is worth investigating whether the target object appears in the background areas of images, even if it is not highlighted as the main observation target. For this purpose, the latest detection algorithms based on machine learning systems, so-called machine learning and neural networks, are employed. For example, convolutional neural networks trained specifically on images of asteroids, comets, and other celestial bodies are capable of detecting faint, barely visible moving sources against the star field. Differential imaging is also widely used, a method where a template star field is subtracted from an image to highlight transient or moving objects that would otherwise remain unnoticed. During analysis, metadata must be carefully checked, as sometimes such objects may appear in images but not be cataloged or stored in databases due to insufficient brightness. As a result, automatic detection systems might miss them or misclassify them, especially if movement causes the object to appear as an artifact or noise. Human analysis of potential findings can play a crucial role in identifying objects that automatic systems often ignore or dismiss as noise, cosmic rays, or random interference. This human factor can be a key link in recognizing genuine astronomical phenomena, particularly when automated algorithms mistakenly classify important signals as false positives. That is why it is essential to establish a collaborative community of civilian specialists and enthusiasts who can work together on verification, analysis, and interpretation of data. Creating such a coalition is a challenging task, as the volume of work is too great for a single person or even a small team. A systematic collaborative effort is required, bringing together amateur astronomers, data processing specialists, planetary scientists, experienced lawyers familiar with scientific research processes, and programmers capable of developing tools for archive data analysis, procedure automation, and information exchange. This team must work in close coordination to ensure tasks are distributed efficiently and results can be freely shared, verified, and utilized by other participants. Modern collaboration platforms are particularly suitable for this purpose, such as GitHub, where source code and algorithms can be shared, Slack or Discord for real-time communication and idea exchange, and cloud data storage solutions that provide access to necessary files and results regardless of location. An important aspect is establishing clear standards for documenting all stages of work, from processing methods to final conclusions. This approach will enable each participant not only to contribute but also to allow others to verify results, thereby increasing transparency and reliability of the entire system. History shows that communities of amateur astronomers and citizen scientists are capable of achieving significant successes in such endeavors. There are numerous examples where volunteer efforts led to the discovery of transiting exoplanets, galaxy classification, or variable star monitoring, all made possible through the collective efforts of passionate amateurs rather than professionals. This experience confirms that combining distributed, often global, efforts with diverse expertise in data processing, observations, and analysis allows for capturing details and patterns often overlooked by individual researchers. Ultimately, collective contributions create additional opportunities for new discoveries and a deeper understanding of the universe. Another important aspect is considering communication channels. If data about potential discoveries exist but are somehow concealed or blocked, there is a possibility that insiders or individuals with access to confidential information are aware of them. In such cases, it is necessary to establish secure, reliable channels of communication that allow for anonymous and safe sharing of critical information. This requires careful planning and organization to prevent misinformation or the spread of false data. Past scientific disputes have shown that real leaks of information sometimes helped uncover important facts or reveal misconduct, so such practices deserve attention. To ensure confidentiality, encrypted communication tools are used, and special protocols for verifying the authenticity of provided data are developed. These protocols should include mechanisms for verifying the authenticity of information without revealing the identity of the source, as well as systems for assessing its importance and truthfulness. Whistleblowers providing information about potential violations or discoveries must be protected both technically and organizationally to eliminate the risk of their identification through metadata analysis or behavioral pattern analysis. An important aspect is preparing for possible false signals. Anonymous channels attract both genuine information and deliberate disinformation. Therefore, checking and verifying any incoming data becomes mandatory. Any statements require confirmation with facts based on verifiable data. For information that appears particularly significant or unusual, convincing evidence must be demanded before taking it seriously or disseminating it to the public. Finally, conducting parallel legal reviews alongside public pressure and initiatives to raise awareness is equally important. Each stage of this process can be viewed as a specific task that utilizes existing tools and procedures, as well as relies on successful examples and precedents implemented in other data archaeology projects or related fields. The main question is whether enough people are willing to invest their time, effort, and knowledge into such an important endeavor. Ultimately, the potential benefit of these efforts could be enormous. If it is possible to reconstruct and present mental images of the atlas, meaning internal images stored in memory or consciousness, in clear visual forms, this could lead to the final resolution of many mysteries associated with this object. Reconstructing high-resolution images of its morphology, determining its structure, presence or absence of a tail, identifying geometric features or external appearance, all of these data are crucial for moving from assumptions to reliable knowledge. Conversely, if such data are absent and forensic examinations yield no results, this is also valuable information. It indicates that research opportunities have been missed, that priorities in planning observations and investigations were set incorrectly, and that the available resources were not fully utilized. These conclusions help determine how to plan future observations, how to properly prioritize missions, what specifically should be observed, and what may not be necessary. Currently, an active phase of searches and investigations has begun. The tools needed for this already exist, and the methods for their use are well developed and understood by specialists. All that remains is to show the will, desire, and determination to achieve the set goals. Public support also plays an important role, since only through joint efforts can success be achieved, as answers to many questions do not come simply from waiting or inaction. They arise as a result of specific excavations, analysis, and in-depth study of collected data. Let us turn to the next part, the experimental tests that could significantly influence our understanding. What new observations could refute or confirm existing hypotheses about the nature of the atlas? Even if we ultimately fail to discover or reconstruct the mental images of this object, we will still have resources and alternative methods. There are a number of observations that we can still carry out. These are experiments and tests that will allow us to distinguish and compare competing hypotheses about what the mysterious atlas truly is. Allow me to tell you about the most important particles of dust that inhabit space, scatter sunlight in very predictable patterns related to their size, composition, and shape. This process is well understood and thoroughly studied in physics. When unpolarized sunlight hits a dust particle, part of the light, after scattering, acquires polarization properties. The degree and direction of polarization depend on the characteristics of the particle itself. Thus, by analyzing the polarization properties of scattered light, we can gain valuable information about the appearance and composition of the scatterer. Metallic or crystalline surfaces, for example, produce their own unique polarization signatures, distinct from those typical of loose, disordered dust aggregates. Smooth surfaces reflect light differently than rough ones, and these differences are evident in polarization patterns. Ice crystals, in turn, have their own characteristic features in polarization behavior, creating recognizable patterns. When observing an object, such as the atlas, one of the well-known cometary bodies, astronomers use what are called phase angles, the angles between the sunlight, the observed object, and Earth. By varying these angles and measuring how the degree and nature of light polarization change, it is possible to determine the surface properties of the comet with high precision. The importance of the phase angle lies in the fact that light scattering behavior depends precisely on the observation geometry. How light interacts with the surface changes at different viewing angles. That is why direct scattering, reflection, and side scattering produce characteristic curves of polarization dependence on this angle. If these curves match those typical of known cometary dust, it confirms the hypothesis of the natural origin of the observed material. The study of cometary dust has been ongoing for over several decades, and during this time, scientists have developed clear expectations. There are certain patterns, for example, how the degree of linear polarization varies at different phase angles, how it depends on the wavelength of light, and how polarization behaves when crossing specific ranges. If, during observations, patterns are found that correspond to metals, ice crystals, or specific geometric structures, this becomes an important anomaly, evidence that the surface properties or composition differ from the norm. Similarly, if an unusually high degree of polarization or special geometric patterns are observed that do not match a random distribution of particles, this indicates the presence of artificial or unusual structures. All the necessary tools are available for such studies. On large ground-based telescopes equipped with polarimeters, precise measurements of polarization characteristics can be conducted. Additionally, if possible, space probes such as the Hubble Space Telescope can be used, provided observation time is allocated. Modern technologies have already reached maturity, and the precision of measurements allows us to distinguish even very subtle differences in polarization behavior, making these studies extremely important. However, this requires setting aside dedicated observation time in advance and carefully calibrating the equipment to eliminate errors and ensure data reliability. Another key method is narrowband imaging during periods when the object is in a quiescent phase. Most of the images of Atlas's atmosphere and gas were taken near perihelion, the moment when the comet is closest to the Sun. This is understandable. The closer the object is to the star, the brighter it appears, and most of the observations are concentrated during this period. However, such focus on studying perihelion poses a risk of missing important information about the processes that stimulate comet activity at more distant positions. To obtain a more complete picture, scientists need to continue observations farther from the Sun, using narrowband filters specifically aimed at detecting certain features. Even at significantly greater distances than initially expected, the comet's activity gradually decreases and diminishes over time. This occurs because, as the comet moves away from the Sun, the energy sources that drive its activity begin to weaken. However, there are cases where emissions of substances continue despite expectations that they should have ceased, or where gas production remains at a relatively high level without clear solar heating stimuli. In such cases, it becomes necessary to seek explanations for these anomalies. It is essential to consider that natural processes, such as heat accumulation inside the comet or radioactive decay of certain elements, can serve as energy sources, causing so-called residual activity. But it is important to remember that these internal mechanisms have their limits. They cannot sustain high levels of gas emissions at very large distances from the Sun. For example, if comet activity were observed beyond 5 astronomical units, that is, approximately 750 million kilometers, that would be quite unusual and would require either an unusual internal composition or an internal energy source significantly exceeding the capabilities of solar heating. In reality, such situations suggest either the presence of exotic materials inside the object or energy sources operating independently of solar radiation. To understand what happens inside these bodies, scientists need to conduct long-term observational campaigns. These include monitoring the comet at various orbits, from perihelion, the closest point to the Sun, to aphelion, the farthest. It is important to record the onset of activity, its peak levels, and then its cessation. This approach allows tracking changes in activity depending on the distance to the celestial body. By comparing activity curves with orbital positions, deviations from expected patterns can be identified. These deviations can serve as valuable clues about the comet's internal structure, the presence of hidden energy sources, or specific features of its composition. The next important step is to conduct in-depth photometric and spectroscopic studies using modern technologies. For example, the application of adaptive optics systems on large ground-based telescopes, such as telescopes equipped with atmospheric distortion correction systems, enables the highest possible resolution of images. An essential technique involves combining dozens or even hundreds of exposures, which significantly enhances sensitivity to faint structures and fine details. This method, known as image stacking, has stood the test of time and proven its effectiveness. By merging multiple images, random noise is averaged out, and the true signal is amplified, revealing details that were invisible in individual frames. To correct atmospheric distortions, adaptive optics systems are used. They measure air turbulence in real time and compensate for these distortions through flexible mirrors that deform according to the received data. As a result, a resolution close to the theoretical diffraction limit is achieved, allowing for the most sharp and detailed images. In addition, it is necessary to request time on space telescopes such as James Webb or the Gottfried Planck to obtain not only spectroscopic data but also high-resolution images. Spacecraft, free from atmospheric distortions, can observe in long wavelength ranges inaccessible to ground-based telescopes, greatly expanding the possibilities for study. If there are any extended structures within ATLAS or similar objects, even very subtle ones, deep high-resolution imaging can reveal their existence. The presence of even the slightest signs of symmetry, geometric features, or structural elements can provide significant insights into the internal makeup of the object. An entirely point-like and perfectly symmetrical source would be extremely unusual, as natural bodies are always characterized by irregularities, defects, and heterogeneities. For example, comet nuclei typically have complex and inhomogeneous internal structures, and the surfaces of asteroids are often covered with numerous craters formed by impacts. The requirements for determining resolution in astronomical observations are very strict. Primarily, it is necessary to detect features or phenomena on such small scales that their sizes can reach tens or even hundreds of meters. This is done in order to understand the nature of the studied object or event with the greatest possible accuracy. Achieving this goal requires either space telescopes capable of observing the universe from orbits or even beyond it, or the largest ground-based instruments equipped with advanced adaptive optics systems that can overcome atmospheric distortions and provide high resolution under ideal weather and technical conditions. One of the methods we consider is the so-called fourth test, which involves coordinated multi-wavelength monitoring. Its essence lies in organizing a large-scale scientific campaign involving various instruments, radio telescopes observing in the radio wave range, satellites detecting X-ray radiation, and optical instruments recording light signals. All of this must occur simultaneously during active observation periods, requiring strict coordination between different scientific institutions and careful pre-planning. Such joint monitoring implies the creation of special committees responsible for allocating observation time to ensure maximum efficiency and synchronization of all participating devices. Organizing such a campaign is reminiscent of a fishing expedition, where having precise nets and advanced tools for catching rare and valuable signals is crucial. The main goal is to identify correlation links between phenomena observed at different wavelengths. For example, if optical light flashes coincide in time with radio pulses, this indicates the presence of electromagnetic activity that goes beyond simple thermal radiation and points to complex processes in high-energy regions. Furthermore, if X-ray flares coincide with gas ejections observed through spectroscopic methods, this suggests the presence of specific plasma processes capable of generating high-energy photons. In such cases, one can hypothesize that complex interactions between plasma particles and magnetic fields are occurring within the system. At the same time, if all these changes happen independently of each other, without clear correlations, it indicates chaotic and possibly random activity, where different processes develop at different times and for different reasons, unrelated to each other. However, if synchronized behavior across various wavelengths were discovered, it would be a very unusual phenomenon and could indicate the presence of organized energy release mechanisms governing these processes. Natural, chaotic events typically do not exhibit close connections across such different ranges of electromagnetic waves, except in cases where a common catalytic factor or energy conversion mechanism links these processes. The frequency of observations and the timescales of phenomena are of great importance in this context. Some manifestations occur within just a few minutes or hours, requiring continuous and uninterrupted monitoring to avoid missing them. Others unfold over several days or even weeks, necessitating the organization of long-term observational campaigns that provide sufficient temporal coverage. This is essential to record both short-term and more prolonged events, as well as to establish baseline characteristics of the behavior of objects or phenomena under their natural activity conditions. For example, there is a fifth test related to monitoring coincidences between neutrinos and cosmic rays. This aspect is more complex, as it requires not only luck but also access to data streams from specialized detectors. Neutrinos are extremely elusive particles because most of them pass through the Earth without interacting with matter. Detecting them requires massive installations located deep underground or beneath ice to reduce background noise and increase the chances of capturing genuine events. Since the flux of neutrinos passing through our planet is very low, most recorded events are. In the modern era of astronomical research, scientists continuously monitor high-energy cosmic rays, aiming to understand the nature and sources of these mysterious and very powerful streams. Each detection of such rays results from an extremely rare coincidence, which can be calculated using specialized statistical methods. By analyzing the frequency of their detection and the observation window, it is possible to determine how likely it is to observe such a coincidence purely by chance, without linking it to any real source. If the number of coincidences recorded over a certain period significantly exceeds the expected value by chance, this becomes strong evidence in favor of a genuine correlation, indicating unusual, possibly high-energy processes. In such cases, the result gains statistical significance, and the detection of this effect prompts a swift reaction from the scientific community, as it signals the emergence of a new, bright, and potentially unique astrophysical phenomenon. Conversely, if the coincidences fall within the range of expected random variation, it is not justified to claim a direct connection to any object or process. In particular, comets and asteroids do not emit neutrinos or cosmic rays within the observable range, which allows their role in relevant observations to be excluded. However, if, for example, a device like ATLAS, or any other similar detector, suddenly detected such streams of neutrinos or cosmic rays, it would mean that the physical processes underlying its operation go beyond the conventional and well-studied models. In this case, it would be necessary to reconsider existing notions about cosmic sources and the mechanisms of their emergence. It is also important to keep in mind that the sensitivity of modern detectors is limited, and if ATLAS does not detect a significant flux of neutrinos or other high-energy particles, unfortunately, we will be left without direct confirmation. Nevertheless, the potential value of such observations is quite high. Even detecting minimal signals would serve as irrefutable evidence that processes capable of accelerating particles to very high energies occur in space. Such a result would fully justify the efforts and resources spent, especially considering that searching for the required data in existing detector databases requires minimal time and effort. Ultimately, even indirect confirmation of such processes could open new horizons in our understanding of cosmic phenomena. Moving on to another important aspect, the analysis of the rotation and light curves of the objects we observe. Comets and asteroids, as is well known, rotate around their axes, and their brightness varies depending on which parts of their surfaces are facing the Sun and the observer at any given moment. These variations are an integral part of their dynamics within our solar system and serve as a crucial diagnostic tool for studying their physical characteristics. A detailed analysis of light curves allows us to determine rotation periods, identify axis orientations, and sometimes even gain insights into the shape of the body. If an object, such as ATLAS, exhibits regular brightness fluctuations, then the period and amplitude of these changes provide valuable information about its shape and rotation characteristics. Short periods, say less than a few hours, suggest that we are dealing with a small, cohesive body that rotates rapidly. Conversely, longer periods spanning a day or more may indicate the presence of a large object or suggest that the body is in a state of tidal locking caused by external influences or internal processes. If the amplitude of brightness variations is very large, it indicates that the object has an elongated or irregular shape, possibly resembling a fragment or a sharply pointed figure. Small variations, on the other hand, point to a more spherical geometry or that we are observing the object from an angle where its surface appears relatively uniform. If, however, the light curve shows almost no changes and remains too smooth, this raises doubts among researchers. Several scientific stations are located at different longitudes, providing round-the-clock and continuous observation. Such multiple placements of instruments allow data collection at any time of day, regardless of weather conditions and lighting, significantly increasing the accuracy and completeness of the analysis. These platforms operate in close coordination, providing continuous monitoring of the studied objects and phenomena, which is especially important when investigating dynamic processes that require constant observation to identify patterns and anomalies. Widely used in analyzing the obtained data are time-tested methods based on determining the oscillation periods and inverting the light curves of sources. These approaches have proven effective in astrophysics and radiophysics, enabling the detection of hidden patterns in brightness and polarization changes. In particular, one of the key tests, TESS 7, involves detecting magnetic fields through the phenomenon of polarization rotation of light or radio waves, known as the Faraday effect. This effect occurs when radio signals pass through magnetized plasma, with the propagation line crossing a region with a magnetic field. As a result, the polarization angle of the radio wave rotates, twists, where the degree of rotation is directly proportional to the magnetic field strength and plasma density in the passage area. This effect, predicted by classical electrodynamics and well observed in various astrophysical conditions, provides a unique opportunity to study the structure and strength of magnetic fields without the need for direct measurement. If an object, such as a hypothetical comet or another celestial body, has its own magnetic field, and its surrounding environment is an ionized atmosphere or coma, then radio signals passing through this region should exhibit a noticeable polarization rotation. The key feature is that the observation geometry requires proper alignment. From Earth, the observed object must pass either in front of a bright radio source or near it to maximize the sensitivity of measurements to the Faraday effect. Such events are relatively rare but predictable. They can be planned and detected using precise orbital calculations and catalogs of known radio sources. An important aspect is the technical complexity of conducting such observations, as it requires extremely precise measurements of radio wave polarization along the line of sight at multiple time points. The measurement accuracy must reach degrees or even fractions of a degree in polarization angle to ensure reliable and precise results. Additionally, it is necessary to account for and correct the influence of Earth's ionosphere, which itself causes polarization rotation of radio waves. This effect can also be measured and compensated for using specialized methods and networks, such as the VBI system, which allows the detection of magnetic fields not inherent to natural cosmic objects. This is particularly important when studying comets, as they lack their own magnetic fields. Their nuclei are often too small and mainly composed of non-metallic substances. The detection of a magnetic field in such an environment would be an extraordinary discovery, indicating either the presence of metallic content inside, the existence of internal dynamo mechanisms, or the presence of electromagnetic systems operating beyond the bounds of usual natural processes. The structure and strength of such a field allow us to narrow down possible models of its origin. Each experiment or test involves different hypotheses and predictions about what should be observed. If the hypothetical object is a natural comet with an unusual composition, expected signs include polarization characteristic of comets, activity that manifests only when heated by the sun, irregular shape and rotation, as well as the absence of multi-wavelength correlations and magnetic field indicators. If, on the other hand, it is a group of fragments or a cluster of objects, one can expect less obvious but still noticeable features. Unusual polarization caused by collective scattering of radio waves, the extent and simultaneous compactness of the structure, chaotic light curves, and the absence of organized electromagnetic phenomena. If the hypothetical object is active due to natural but extraordinary circumstances, then the detection of such features would strongly suggest a natural origin, whereas the presence of organized electromagnetic signals would point toward artificial or technologically influenced sources. Ahead for ATLAS lie new perihelion passages, periods of activity, and fresh opportunities for observation and analysis. The only question is whether the scientific community will take these opportunities seriously and whether it can overcome skepticism or ambiguous assessments, turning them into real steps forward. Otherwise, ATLAS risks remaining merely a footnote in the catalog of interstellar visitors, without further recognition or comprehensive study. If we assume that everything happening is not a coincidence but the result of artificial influence, then science and politics face an entirely different challenge. In that case, there will be no room for the usual methods and protocols used in the search for extraterrestrial intelligence. Even hypothetically, if the third object of ATLAS is not a natural formation, everything would change dramatically. This would require a revision not only of the methods employed but also of the entire response strategy, goal setting, regulatory procedures, and confirmation protocols for such unique and extraordinary discoveries. The first step should be to revisit the protocols adopted within SETI programs, the search for extraterrestrial civilizations. The traditional approach to SETI focuses on detecting radio signals and beacons that could be intentionally transmitted by technological civilizations seeking contact. It was assumed that such messages are deliberate, utilize electromagnetic radiation at specific frequencies, and originate from planetary systems around other stars. However, if technology advances to the point where artifacts can travel between stars and are small and numerous enough for us to detect them within our own solar system, then the entire search paradigm would change radically. In this case, these objects would not necessarily transmit signals or send messages to attract our attention. They could exist in a passive state, simply observing their surroundings, or operate based on principles entirely different from our familiar forms of communication. Detecting them would be more about identifying anomalous physical properties or behaviors incompatible with natural processes, or discovering objects whose characteristics do not fit existing models. This means that the search methodology must shift from traditional radio telescope-based approaches to investigations in optics, spectroscopy, astrometry, and other fields capable of helping identify anomalous objects among millions. The possibility of conducting direct studies of their nature opens broad horizons for scientists. We can gather numerous confirmations, conduct various tests and experiments. However, some of these objects simply cannot be detected through radio signals or other conventional verification methods. In the modern scientific and technological context, a crucial question arises. Does the behavior of this object in all observed aspects and across different modalities, whether visual, radar, or others, more closely resemble artificial models rather than natural phenomena? In other words, to what extent do its manifestations align with models associated with intelligent activity, and to what extent with natural processes? These questions are increasingly pressing on the political stage, becoming the subject of urgent discussions. If the existence of the artifact is confirmed, a natural question arises: who owns the data obtained? Who has the right to manage the materials confirming the presence of some unidentified object if it is indeed verified? Currently, most space agencies maintain full control over information about their missions and discoveries. They determine when and how to share results, what information to disclose publicly, and under what conditions. However, if the discovery involves technologies that do not belong to humans and go beyond known sciences and technologies, the situation becomes more complicated. In such cases, various jurisdictional disputes may arise, as not only national interests but also international agreements and legal norms regulating space activities are insufficiently clear and unambiguous. National security and defense organizations can undoubtedly claim control over such discoveries, since they may pose threats or become strategic assets. At the same time, international bodies, such as the UN Committee on the Peaceful Uses of Outer Space, could assume responsibility for coordinating such events and decisions. Unfortunately, the legal frameworks governing the processing and dissemination of information about such discoveries currently lack the necessary clarity and effectiveness. Existing protocols for disclosing scientific information, which could serve as guidelines, remain vague and incomplete. The International Academy of Astronautics has developed the so-called SETI principles, a set of recommendations designed to determine how to proceed upon detecting artificial signals or other signs of extraterrestrial technology. These principles emphasize the importance of international notification and thorough scientific verification before sharing information with the public. But it is important to remember, these recommendations are merely voluntary guidelines, not mandatory rules. Moreover, they were created with the detection of radio signals in mind, not physical objects or artifacts, which makes them insufficiently universal for new discoveries. If a spacecraft captures images showing something that clearly appears to be an artificial object, who makes the decision about when and how this information becomes available to the public? In this case, the chain of data storage and verification becomes particularly important. How can we be confident in the authenticity and genuineness of the message? Any claim of artificial technology will inevitably face strong skepticism, which is a natural and justified response from the scientific community. To overcome such skepticism, it is necessary to rely solely on data that leave no doubt about their integrity and authenticity. For example, raw materials recorded without interference, with cryptographic headers confirming their origin, or multiple independent observations corroborating the same phenomenon. Transparency is crucial. Open data repositories accessible to anyone for analysis, and thorough documentation of each stage of information processing. Only in this way can full trust in the results be established. Otherwise, any attempts to interpret the data as erroneous, fraudulent, or incorrect will become an integral part of the discussion. International coordination in such situations is essential but comes with significant challenges. Different countries have their own interests in space exploration and often adhere to different approaches regarding transparency and access to information. The discovery of a new structure, especially one that seems unusual or even mysterious, can be compared to great discoveries of the past, such as the unveiling of the double helix of DNA or the first visualization of an atomic nucleus. These achievements required not only individual scientists' efforts but also large-scale international cooperation, pooling resources, knowledge, and expertise. At the same time, their successes were not limited to technology and experiments. They also prompted the development of new policies, ethical guidelines, and codes of conduct for the scientific community. After all, when it comes to such significant discoveries, complex questions related to morality, responsibility, and the boundaries of human intervention always arise. Even these analogies do not fully convey the scope. Modern challenges have gone beyond traditional frameworks. Ethical issues are increasing day by day. For example, if we assume that an artifact or a form of unknown technology truly exists, the question arises: who owns it? Does the person who found it or gained access to it have the right to consider it their personal property? Or is it perhaps the property of all humanity, and its study should be conducted in the interests of the entire global community? Or maybe such an object or phenomenon was sent from someone or something outside, raising the question: who and how should decide whether it can be touched, studied, or contacted? Furthermore, it is possible that what we have discovered is not merely a random phenomenon, but an object or signal that is being observed from the outside. If so, an even more important and dangerous question arises: what if this observation is already underway? What if our interference or attempts to understand it provoke a reaction that exceeds our current understanding and predictions? Science fiction has long explored scenarios where such situations lead to unpredictable consequences, but in reality, these concerns are not merely fictional. This is a challenge that requires a serious and responsible approach, as the potential consequences could be very serious. If we assume that we are indeed encountering something unusual, there is a risk of premature claims and hasty conclusions. For example, if someone were to claim the existence of highly advanced artificial technologies based on insufficient evidence, it could seriously undermine trust in the scientific community and in research in this field. Such claims might provoke skepticism, ridicule, or even distrust among the public, negatively affecting future efforts to search for extraterrestrial civilizations or develop SETI technologies. As a result, verified and reliable evidence could be called into question, and further discoveries might be difficult to take seriously. At the same time, relying solely on evidence and demanding increasingly higher standards of credibility is not always reasonable, especially if the facts or phenomena we observe truly exist and are important for understanding the world. In such cases, excessive delays in confirmation or overly complicated criteria for evidence can hinder progress. Therefore, it is crucial to find the right balance, to be able to assess risks, maintain scientific integrity, and at the same time not lose sight of the possibility of discovering something truly significant. This requires making complex, often subjective decisions, since not everything can be reduced to strict formal rules or algorithms. It is especially important to consider society's reaction, as the results of scientific research and their consequences directly influence public consciousness. Imagine how the discovery of a technology or object unlike a human could affect people's worldview. Some will be thrilled, seeing it as humanity's greatest achievement capable of changing history. Others may panic, fearing invasions or threats to their safety, their lives, and their existence. Still, others, despite convincing evidence, will remain skeptics, viewing everything as a mystification or a carefully concealed conspiracy. Managing these social consequences is arguably the most complex task facing modern scientists and government structures. It is evident that our existing systems, institutions, and protocols are not fully capable of preparing us. There are certain boundaries and frameworks that define the structure of our understanding of the world. These boundaries are not created randomly but are deliberately established by laws and principles that we must follow. It is important to remember that all we need to do is adhere to these frameworks, applying them consistently and systematically to our research and observations, even if such an approach leads us to face unpleasant or uncomfortable consequences. The reality is that we are already involved in this process, and whether we realize it or not, we are on a path of exploration and discovery. Every observation we make, every attempt to understand the properties of the atlas, and every analysis of its behavior are integral parts of the overall quest for truth. Often, we do not approach this question with the level of systematic persistence and focus it deserves. The question is whether we will continue making fragmented, uncoordinated observations that only leave uncertainties and do not provide definitive answers, or whether we will organize a targeted, coordinated scientific campaign aimed precisely at finding conclusive and convincing explanations. If Atlas is an artificial object, we will inevitably find out sooner or later. The technologies we possess leave traces that cannot be hidden forever. Its structure, composition, and behavioral models will eventually become apparent with enough observations and research. The only question is how much time it will take and how many opportunities we will lose due to fluctuations, random errors, or disorganization in our actions. And if it turns out that Atlas is not an artificial object, that too will be a valuable and convincing piece of evidence. It will open new horizons for us, showing that through the spectrum of natural phenomena created by the universe, we can uncover new, previously unknown patterns. In any case, the very process of investigation advances science, stimulates the development of detection methods, improves data processing, and leads to the creation of increasingly accurate and complex models. Moreover, such research prompts us to think about how we recognize signs of intelligence in space, especially if we encounter it in an unexpected or unfamiliar form. These questions are important and relevant regardless of whether Atlas turns out to be a natural or an artificially created object. It is part of a broader picture of the cosmos that is unfolding before us. Has a new era begun, filled with increasingly astonishing and strange phenomena? To understand this, we should take a step back and look at the bigger picture. Currently, we have three unusual objects, Comet Atlas, each behaving completely differently from everything we have observed before. These extraordinary bodies evoke special curiosity among scientists. Next, we observe a phenomenon called escape J1832, which pulsates in the radio and X-ray bands with a period of approximately 44 minutes. This regularity does not match the characteristics of known classes of astronomical objects. In addition, we have a detector registering neutrinos with an energy of 220 electron volts, indicating particle acceleration processes that are currently impossible to fully explain. Are these phenomena isolated anomalies, or are we on the brink of an era when the universe proves to be stranger and more mysterious than we previously thought? It is important to ask ourselves this question because significant changes have occurred in the field of astronomical research over the past 10 years. Modern survey telescopes such as the Zwicky Transient Facility, Pan-STARRS, and the Vera Rubin Observatory scan vast areas of the sky repeatedly, capturing everything that changes, moves, or suddenly flares up. Radio telescopes like ASCAP and MEERKAT operate continuously, monitoring the celestial space in real time and detecting transient events that were previously missed due to the limitations of instruments. Neutrino detectors have grown from small experimental setups into massive devices. Until recently, the hypothesis of neutron-star mergers was regarded more as a theoretical conjecture and modeling assumption, since there was no direct observational confirmation of such events. However, everything changed in 2017, when astronomers managed to detect one of these mergers for the first time through joint analysis of gravitational waves and electromagnetic radiation. This landmark event became a real breakthrough, confirming that neutron stars can merge and that such events leave a noticeable imprint across different spectra of observable signals. It was precisely thanks to this synchronized detection, when highly sensitive instruments recorded gravitational waves and, simultaneously, telescopes observed electromagnetic flares, that we were able to confirm the existence of such systems for the first time. Let us consider why this discovery had such an impact. Its significance lay in demonstrating how modern observational tools, combined into a unified chain, allow us to expand the boundaries of our knowledge about the universe. All this science is developing because we now have the ability to see further, or more precisely, to hear and sense what was previously beyond reach. And all of this has become possible because our instruments and technologies are improving every year. As a result, the universe continues to surprise us with astonishing discoveries, because now we observe it with much greater sensitivity and coverage than ever before. Scientific progress in this area is actively accelerated by advances in machine learning and artificial intelligence. These modern technologies enable the automatic analysis of vast amounts of data, which was previously impossible to perform manually within reasonable timeframes. AI-based algorithms can scan millions of images, spectra, and light curves, identifying patterns and anomalies that would take humans years to detect. As a result, the discovery of unusual events occurs much faster than their full explanation. This creates a situation where the number of recorded anomalies significantly exceeds our capacity to understand their nature. The catalog of unexplained phenomena grows much faster than the list of those that have been classified and understood. It is worth noting a paradox: the more data we collect, the more noise and false positives we encounter. Increasing the number of observations leads to a rise in statistical errors and the appearance of artifacts, distortions caused by measurement instruments that are mistakenly interpreted as real signals. Consequently, the number of false positives grows proportionally with the scale of the data. When dealing with billions of objects, even a very small chance of a random event means such events can occur thousands of times within a single study. Therefore, an important question arises: how can we distinguish truly new physical phenomena from random fluctuations caused by errors or statistical variations in large datasets? The answer lies in using correlation analysis and replication methods. If anomalies are concentrated in specific categories of objects, localized in particular regions of space, or observed during certain periods, these signs suggest they may have a genuine physical origin. For example, if unusual signals appear only from certain types of stars or in specific parts of the sky, this indicates a real correlation or pattern. Conversely, if similar anomalies occur chaotically, happen only once, and do not recur, they are likely the result of noise or random errors. For instance, a unique object known as ATLAS, or an astronomical object designated ASCAP J1832, may be unusual, but if it does not reappear in subsequent observations, it is probably just an isolated anomaly. The same principles apply to neutrinos. If only a single event is recorded, it does not necessarily indicate the presence of a new force or process. The question then arises: are these phenomena related to each other, or are they merely coincidental? Is there a possibility that we are overlooking something? The universe has always seemed mysterious and wondrous to us, filled with secrets that remain beyond the reach of human understanding. However, only in recent years, thanks to advances in science and technology, have we begun to realize more clearly how deep and multifaceted this mystery truly is. Perhaps we previously underestimated it, considering it merely as deviations from familiar models, but now we can confidently say that the very nature of the world often exceeds our notions. In other words, we are starting to understand that our perceptions and theories are only approximations of the truth, which may be far more complex and strange than we had assumed. Or perhaps, the very idea of strangeness is relative. After all our observations and models are based on certain assumptions and limitations. The more refined our scientific theories become, the more they incorporate what once seemed strange, and it becomes part of the norm. Therefore, it is possible that cosmic strangeness is merely a matter of scale and our level of knowledge. It is also conceivable that reality itself does not have to conform to human intuition or outdated 19th-century notions of physics. For example, quantum mechanics, which today appears very strange compared to the classical worldview, has long been a fundamental part of modern science. Its principles, superposition, uncertainty, non-locality, evoke wonder and raise many questions, yet they are the key to understanding the micro-world. Similarly, the theory of relativity, which revolutionized our ideas about time and space, also appears unusual and even strange until we learn how to apply it and comprehend its internal logic. Moreover, phenomena such as dark matter and dark energy, mysterious components of the cosmos, remain completely unexplained to this day. Their existence is confirmed only indirectly, and their nature seems extremely unusual and even strange. Each new generation of scientists discovers that reality operates according to laws that surprise and challenge our conventional notions, and these laws often seem incredible until we learn to control or understand them. Even after we begin to grasp these principles, they continue to seem strange. They keep astonishing us with their complexity and unusualness, as if our universe is an endless source of new mysteries. In this sense, perhaps we are living in an era of unique oddities, a time when science reaches new heights in exploring and understanding the surrounding world. Today, we have the opportunity, through modern technologies and tools, to see the universe as it truly is, in its entirety, across all scales, under extreme conditions, at incredible energies that push the laws of physics to their limits. We are now on the verge of a discovery that could completely change our perspective on space. Phenomena such as the cosmic object ATLAS, as well as sources of high-energy neutrinos, are only the first hints of a much richer catalog of unusual cosmic phenomena yet to be uncovered. They may serve as beacons indicating the existence of a whole world of strange and astonishing processes hidden deep within the universe, which currently remain beyond our observational capabilities. On the other hand, perhaps we are too focused on finding patterns in random phenomena, too inclined to see regularities in space where none truly exist, allowing our imagination to operate within the realm of hypotheses and assumptions, often ahead of actual data. The only true path to the truth is to continue observing, keep testing our hypotheses, and subject our theories to rigorous and systematic verification through precise measurements and experiments. Science is a constant movement forward that does not fear making mistakes, because it is through errors that we realize our understanding of the world is still imperfect and that we can adjust our course of research. There is no doubt that we are experiencing a remarkable era in the history of astronomy and cosmology. The volume of discoveries is growing at an incredible rate, and each new investigation brings not only new knowledge but also a sense of wonder and curiosity. This discovery simultaneously evokes excitement and concern because it indicates that the universe continues to keep its secrets, not revealing all its mysteries and not exhausting the astonishing surprises it can offer. Every time we think we have understood much, new facts and phenomena emerge, and our understanding of space becomes increasingly complex and multifaceted. This situation highlights that there are still unexplored regions at our disposal, and the riddles related to the nature and behavior of celestial bodies await their decipherers. In this sense, we can say that the universe possesses a power and potential capable of fundamentally changing our beliefs and views, forcing us to think more deeply about what is truly possible and what remains on the edge of fantasy. Reflecting on recent research, it is worth noting that we have reached an important point: the so-called final synthesis of our knowledge and hypotheses. At this stage, it is necessary to understand precisely what we know for certain, what requirements can be imposed on our theories, and how this knowledge can be tested. Ultimately, we need to come back down to earth to make a clear summary, to separate facts from assumptions, to establish what is confirmed by observations and what is merely speculation, and based on that, to determine the next steps in research. So, what constitutes our solid knowledge? First, thorough testing was conducted, including processing over 9,000 frames obtained with instruments part of the ATLAS III system. As a result of this analysis, scientists found no signs of an extended coma in the object under consideration, perceiving it as a point source without indications of a complex structure. These results are highly reliable and reproducible, indicating a high degree of accuracy in the data obtained. Second, large space telescopes such as the James Webb, along with other infrared instruments, detected gas emissions, particularly carbon dioxide and water vapor. These observations point to the presence of volatile substances, their activity and dynamics, suggesting complex processes occurring inside or near the object. Despite some contradictions, this data is well-founded and trustworthy. However, there are less definitive pieces of information. Ground-based optical telescopes yielded varying results. Some detected asymmetry in the object's structure, while others found no signs of internal or external structural features. These observations, although real, highlight discrepancies in the data. At the same time, observations conducted by the Psyche spacecraft, which could help resolve these contradictions and provide a clearer picture, have not yet been published, so we cannot be certain whether they exist at all. What remains unclear and raises questions. First, the physical mechanism behind gas formation without an obvious dust tail is a mystery, since most similar objects display such tails associated with solar wind. Second, the composition and structure of this celestial body's core, as well as the processes governing its behavior. The contradictions found by different instruments may not necessarily indicate anomalous behavior but could rather result from observational bias or differences in data processing methods. It is also important to understand whether electromagnetic or plasma phenomena play any unusual role in this process. Furthermore, there is the question of the connection between the multi-wavelength effects we discussed and the so-called ASCAT J1832 high-energy neutrinos, and the possible link to data obtained through the ATLAS system. However, it should be emphasized that many of these considerations are merely hypotheses or assumptions based on current data, not confirmed facts. They require further investigation and verification before they can be considered an accurate picture. This entire field remains open for new research and experiments. Now let's move on to the most important part. In this context, there are three key and decisive tests that can determine the fate of this mysterious situation and help us understand the true nature of what is happening. Each of these tests represents an important step in the investigative process, and their sequential execution will allow us to obtain the most complete and objective picture. Let's examine each of them in detail to understand their essence, methods, and expected results. The first test is based on the use of archival forensic and restorative research data. In other words, it involves accessing information that can be obtained from data stored in archives, as well as the possibility of reconstructing images and details related to the spaceship, Psyche, or any other observations recorded during the observation windows known as the ATLAS. This stage includes gaining access to existing data, systematically analyzing it, and checking for images related to the object of interest. It is important not only to find such images but also to thoroughly study their structure and morphological features. This will help determine what the object looks like in reality, its shapes and sizes, and how much it differs from known celestial bodies or objects. Additionally, it will be necessary to verify the authenticity of the metadata, that is, the data about the date, time, conditions of shooting, and the history of image processing, to exclude possible errors or falsifications. This approach is considered the most direct and convincing because high-resolution images provide a real view of the investigated object. With this, it is possible to identify whether it is a typical or regular core, a debris cluster, or some geometric formation, such as a spheroid or an asymmetrical structure. The technical barriers to implementing this test are usually low. With access to archives and the necessary tools, it can be conducted relatively easily. However, institutional barriers related to access restrictions or bureaucratic procedures may be quite high. In such cases, persistence, prolonged requests, and interaction with official bodies will be required to obtain the necessary permissions. Ultimately, conducting this test will provide the most objective picture of the object's appearance and help establish its authenticity. The second test involves organizing and conducting multi-wavelength coordinated observations. In other words, it entails launching a large-scale campaign during the next active period of the ATLAS, which is associated with increased activity of the observed objects. At this stage, it is necessary to organize comprehensive monitoring using various instruments and methods. Primarily, optical and infrared observations are planned using polarimetric and spectroscopic tools. This will enable monitoring of gas production, as well as the detection of potential substance emissions or changes in the atmospheric composition of the object. Radio telescopes used for studying radio waves will help detect radio signals and bursts associated with the object's activity. X-ray observatories will be employed to register flares and high-energy events, providing insight into whether the object exhibits any high-energy activity. Equally important are particle detectors, which can track coincident high-energy events that could indicate nuclear or cosmic processes. This comprehensive approach, combining different observation methods, will allow the identification of correlations and interconnections that are typically overlooked when using only a single instrument. Specifically, it will help determine whether ATLAS exhibits electromagnetic activity and whether its behavior is periodic or chaotic. It is also crucial to identify whether it creates any signatures or features that go beyond the usual characteristics of comets or other known cosmic objects. As a result, such an integrated monitoring system will provide a more complete understanding of the nature of the object's activity and its possible mechanisms. The third phase involves monitoring and analyzing high-energy events related to this object. During this stage, continuous data collection from neutrino detectors, cosmic ray networks, and gamma-ray observatories is necessary. The goal is to identify any statistically significant correlations between ATLAS activity and events occurring in space involving high-energy phenomena. An engagement strategy is key to involving everyone interested in this field. Anyone with at least basic knowledge of data science can contribute by assisting in archival research and developing new analytical tools. These specialists, equipped with their skills, can process and interpret the accumulated data, significantly accelerating progress. If you have access to telescopes, even small amateur instruments, you can become part of joint observational campaigns. Such efforts unite professionals and amateurs, enabling more extensive and precise observations of celestial objects and collecting valuable information about unpredictable phenomena. Participating in these campaigns offers an opportunity to personally contribute to important scientific work, as every observation made at the right moment could be crucial. If you have expertise in law, your experience is invaluable for preparing applications and procedures to gain access to necessary data. You can assist with document preparation and requests to ensure unobstructed access to information that may shed light on the mysterious object or phenomenon. After all, proper documentation and knowledge of procedures are essential components of successful research. Moreover, if you have a platform or an audience, you can play an important role in raising public awareness about what is happening. By sharing current discoveries, mysteries that require explanation, and the need for transparency in scientific research, you create pressure on institutions and scientific organizations, encouraging them to be more open. This is important because public attention fosters the development of science and helps attract additional resources. If you have funding, consider supporting citizen science through grants or crowdfunding projects. Your financial assistance can serve as a catalyst for new research, the development of unique methods, and the expansion of existing programs. Every contribution, even the smallest, helps accelerate the process from mystery to clear answer. Each of these contributions is a building block in the overall picture that brings us closer to a solution. The emotional aspect of this story is also significant. We stand on the threshold of a discovery that could fundamentally change our understanding. We have an object that behaves unusually, raising many questions among scientists, and there are technologies capable of helping us find answers. We face a choice: either accept it as a simple and strange comet, continue observing and move on, or admit that we do not fully understand what is happening so far and try to understand the reasons for this anomalous behavior. The most familiar and easiest path is to simply call this phenomenon a strange comet and leave everything as it is, without delving into further research. But the more complex and respectful approach is to acknowledge that we cannot yet explain what is happening and to make efforts to uncover the causes. It is precisely these moments that drive scientific progress. When observations begin to contradict existing theories, when the standard model of our universe appears to be cracking under the pressure of anomalous data, a choice arises. Either try to fit the model to new facts with special assumptions or question its fundamental validity and consider the need to rethink core principles. In most cases, thanks to scientists' persistence, the standard model undergoes improvements and becomes increasingly accurate and reliable. It survives, strengthening itself through new discoveries and adjustments. However, sometimes, very rarely, anomalies are so significant that they require a complete overhaul of the entire knowledge base. At such moments, situations arise where familiar explanations no longer work, and new hypotheses, sometimes radical and revolutionary, must be sought. We do not yet know for certain which scenario is correct. Perhaps it is a comet with an unusual but ultimately explainable nature. Or perhaps this is the first vivid example of something we have yet to classify, a natural but exotic object that doesn't fit into our usual frameworks. Or maybe it's about a scene that sounds like science fiction, a possible first detection of the artifact. Atlas mystery offers each of us a unique opportunity to become participants in this fascinating and instructive process. It's as if it invites us to delve deeply into research to understand what is truly real in our world and what are merely false interpretations created by human perception or misconceptions. This challenge requires not only curiosity but also a willingness to question previously accepted beliefs, test their validity, and verify whether they are true or false. So, let's not be passive observers, but take responsibility for exploring this mysterious world. First, it is necessary to request relevant data, gather facts, evidence, and research results that are available or can be obtained. After that, it's important to conduct thorough observations, to watch phenomena and processes, because observation helps reveal the true nature of things. The next step is to perform analytical work, systematize the collected information, identify patterns, and draw conclusions based on logic and scientific methods. Only in this way can we understand what the universe is truly telling us, what secrets it hides, and what answers are already within our reach. The most frightening and perhaps the most dangerous aspect of this process is to make mistakes in our assumptions on crucial issues, because this can lead to incorrect conclusions and a distorted worldview. However, it would be much worse not to notice our mistake at all and to continue living without questioning or seeking to understand the truth. Therefore, the boundary of possibilities is open, and all doors are wide open before us. The mystery continues to await its solver. And somewhere within the data we have yet to see, in the observations still to be conducted, that is where the answer is hidden. It waits until it is found and understood, for knowledge is the key to unlocking the deepest mysteries of existence.